We are born into a world defined by its one-way processes. A glass shatters on the floor, but we never see the shards leap back together to reform the glass. A star explodes in a brilliant supernova, scattering its elements across space. But we do not witness those elements rushing back to remake the star. This directionality, this forward march is what we call the arrow of time. It is the narrative thread that connects every event. This arrow seems to be governed by a powerful principle, a rule that appears to hold sway over everything, from a cup of coffee cooling on a table to the ultimate fate of galaxies. This governing principle is known as the second law of thermodynamics, and its central character is entropy. Entropy is often described simply as a measure of disorder or randomness. The second law states that in any isolated system, the total amount of entropy can never decrease over time. It can only stay the same, or, more likely, increase. This law seems to be the engine driving time's arrow. Looks so different from the future. A state of higher entropy. It is the reason why yesterday's order inevitably gives way to tomorrow's mess. And so, we perceive time as a story of decay and dispersal. We watch mountains erode, buildings crumble, and memories fade. The universe itself seems to be on a one-way journey from an incredibly ordered state at the Big Bang towards a final uniform state of maximum entropy, often called the heat death of the universe. This perspective is powerful, and it aligns perfectly with our everyday experience. But what if this experience, this perception of a one-way street, is hiding a deeper, more subtle truth about the nature of reality? To understand the arrow of time, we must first become familiar with its constant companion, entropy. Let us paint a picture. Imagine a brand new deck of cards, perfectly ordered by suit number. This is a state of very low entropy. It is highly organized and predictable. Now shuffle that deck just once. The order begins to break down. With every shuffle, the system moves towards a state of higher entropy, greater disorder. It is far more likely a shuffled deck will be randomly mixed than perfectly ordered. This simple example reveals the statistical nature of entropy. It is not that a shuffled deck cannot return to order, it is just astronomically improbable. There is only one way for perfect order, but countless trillions of ways to be disordered. The universe, an immense deck of particles, is constantly shuffled. It moves from less probable ordered states to much more probable disordered states. This is the second law of thermodynamics in action, overwhelming probability. You place an ice cube into a glass of warm water. The ice cube is a small region of order, molecules in a crystalline lattice. The warm water is more disordered, molecules moving freely. Inevitable, heat flows from the warm water to the cold ice, and the ice melts. The ordered ice molecules mix with the rest, and the system settles at a uniform, lukewarm temperature. Total entropy, overall disorder, has increased. We never, ever see the reverse happen on its own. Now, let us zoom in, leaving the world of melting ice shuffled cards behind. Let us travel down to the microscopic realm, the world of atoms and subatomic particles. Here, where the fundamental laws of physics play out, we find something astonishing. The rules that govern interactions of these tiny constituents are time-symmetric. That means the equations work just as well forwards as backwards. The laws themselves do not contain an arrow of time. They have no preference for past or future. Imagine filming a collision between two billiard balls. Imagine two atoms. Play the film forward. You see them approach, collide, bounce away. Run the film in reverse. Approach from final paths, collide, move back along their initial paths. This question is old. 19th century physicist Johann Loschmidt posed it. He said, if every atom's motion is reversible, the gas's behavior should be reversible too. A gas expands to fill a container, increasing entropy. But there exist initial velocities that would make atoms gather back, decreasing entropy. So why do we only see expansion? Why does nature seem to forbid large-scale entropy decreases? The answer emerges when we see the gap between microscopic reality and macroscopic description. Time-symmetric laws apply to the precise state of every particle, exact position, exact velocity. But we never have access to that complete information. We do not track every one of the trillions of atoms in a gas. Instead, we measure bulk properties: pressure, volume, temperature. These macroscopic descriptions are coarse-grained averages. This is where the illusion of irreversibility begins. A single macroscopic state can correspond to an immense number of different microscopic arrangements. The connection between entropy and our lack of knowledge is one of the most powerful ideas in modern physics. This concept was formalized in the 20th century by Claude Shannon, the father of information theory. He showed that entropy is not just a measure of physical disorder, but also a measure of missing information, or uncertainty. The more microstates that could correspond to the macro state you observe, the less you know about the system's true configuration, and therefore, the higher its entropy. The second law of thermodynamics can thus be rephrased in a striking way. It becomes a statement about our knowledge. It says that as a system evolves, it tends to move into macroscopic states consistent with a larger number of microscopic arrangements. Because we are ignorant of the precise microstate, this evolution looks to us like an increase in randomness and a loss of order. The arrow of time, from this perspective, is not an objective property of the universe, but a consequence of the coarse-grained, incomplete way in which we perceive it. It is an arrow of increasing ignorance, Imagine a vast library containing every possible book. One book is a perfectly written story. All the other books are random collections of letters. If you pick a book at random, you are overwhelmingly likely to pick one of the gibberish ones. Similarly, the universe in its evolution is moving from a highly specific, low-entropy state, the single-story book, to one of the vastly more numerous, high-entropy gibberish books. It's not that the laws of physics forbid the gibberish from rearranging into a story. It's just that there are so many more ways to be gibberish. This information-based view of entropy changes everything. It suggests that if you could somehow know the exact position and momentum of every particle in the universe, the concept of entropy would lose its meaning. For such an all-seeing observer, the universe would be like a perfectly functioning machine, evolving according to time-reversible laws. There would be no arrow of time. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The mystery of time is not a closed book. It is an open invitation to look deeper. This journey into the heart of time and entropy can feel abstract, but it touches upon the very fabric of our reality. It challenges us to see the world not just as a collection of objects, but as a dynamic interplay of information and observation. The ideas we have explored suggest a universe that is far more subtle and interconnected than it appears. If you find these concepts as fascinating as I do, take a moment to engage with them further. Pause to consider the implications. And if you enjoy explorations like this, which connect the cosmos to our own experience, I invite you to subscribe and join us for future journeys into the mysteries of science. The thought that time's arrow is tied to information has profound consequences. It means that every act of forgetting, every loss of a record contributes to the forward march of time. Our memories, which are stored information about the past, are what create a personal sense of temporal direction. We remember the past, but not the future. This asymmetry of knowledge, this informational divide, may be the most intimate experience we have of the second law. We are, in a very real sense, information processing beings swimming in an informational sea. Thinking about these ideas can shift our perspective. When you next watch cream swirl into your coffee, you can see it not just as a simple act of mixing, but as a manifestation of probability and missing information. You are witnessing the system move into a more likely, higher entropy state because you cannot track the motion of every individual molecule. The seemingly irreversible act is a reflection of your own macroscopic viewpoint. It is a beautiful, everyday demonstration of one of the deepest principles in the cosmos playing out in your coffee cup. So, let us continue our exploration with a sense of wonder. The universe does not give up its secrets easily, but by asking these deep questions, we expand our own understanding. We learn to appreciate the hidden layers of reality that lie just beneath the surface of our perception. the relationship between the quantum world and the classical world, between information and reality, between the observer and the observed, is where the next great scientific revolutions are likely to be found. The mystery of time is not a closed book. It is an open invitation to look deeper. The link between entropy and information becomes even more profound when we consider the role of the observer in quantum mechanics. In the quantum world, the very act of measurement, the act of gaining information about a system, can fundamentally change it. Before we look, a particle can exist in a superposition of many possible states at once. When we measure it, this cloud of possibilities collapses into a single, definite outcome. Information about the other possibilities is effectively lost to us, and this act of observation can look like an irreversible event. This suggests that the arrow of time may be deeply entangled with the act of observation itself. Perhaps entropy increases for us because we are constantly interacting with the world, making measurements, and collapsing quantum possibilities. Each interaction leaves us with a definite record of one outcome, while the information about what could have been is scattered and lost. Our reality, the one we experience, is a long chain of these irreversible seeming measurements. The arrow of time might be the trail of these collapsed wave functions we leave in our wake as we move through the quantum realm. Consider quantum entanglement. Two particles linked so their fates are intertwined, even when they are far apart. If you have an entangled pair and only observe one particle, your knowledge of the overall system is incomplete. The part of the system you are ignoring will seem to grow in entropy from your perspective. Some physicists propose the thermodynamic arrow of time emerges for any subsystem of a larger, time-symmetric quantum universe. We, as observers, are always subsystems. Therefore, the irreversibility we see, the breaking egg, the melting ice, the dying star, might be a shadow cast by our own limited interaction with the whole. The universe as a complete, closed quantum system may be evolving in a perfectly reversible way, like a timeless quantum computer processing information. But we, as parts within that system, can only access a fraction of that information. The entropy we measure and the time we experience are features of our particular, partial perspective. They are real for us, but they may not be the ultimate reality. We arrive at a place of profound mystery and hopeful curiosity. We began with the simple, everyday experience of time flowing in one direction. We journeyed through the statistical nature of entropy, the time-symmetric laws of the microscopic world, and the deep connection between entropy and information. The picture that emerges is one where the arrow of time is not a rigid, fundamental law etched into the cosmos, but rather a perceptual phenomenon, an emergent property that arises from our interaction with a reality far more complex than we can fully grasp. This perspective does not erase the second law, it reframes it. The law remains an incredibly powerful and accurate predictor of the world we experience. Engines will still run, stars will still burn out, and our coffee will still get cold. But understanding its potential origins in information and observation opens up new frontiers. It suggests that the boundary between the knower and the known, between mind and matter, may be more blurred than we ever imagined. The arrow of time may be pointing not from a universal past to a universal future, but from what is known to what is unknown. This leaves us with a gentle yet deep question. If the arrow of time is indeed a feature of observation, a consequence of our limited knowledge, then what is the universe like when no one is looking? In a cosmos without coarse-grained observers like us, would there be any distinction between past and future? Does a river truly flow if there is no one there to see which way the water is going? The universe might be a vast, timeless quantum state, a shimmering ocean of possibilities where the concepts of before and after have no inherent meaning. And so, we are left to wonder. Perhaps reality is a participatory symphony, and the flow of time is the melody that we, the audience, create by listening. Our very existence as information-gathering beings might be what crystallizes the timeless quantum foam into a story with a beginning, a middle, and an end. The mystery of time is not just a puzzle for physicists, it is an invitation for all of us to contemplate our own place in the cosmos. What is the true nature of the river we call time? And what role do we play in charting its course? Maybe the arrow of time isn't a property of the universe, but a shadow cast by our own observation. The mystery of time is not a closed book. It is an open invitation to look deeper. Right now, you are sitting still. Or so it seems. But the truth is far more dramatic. You are hurtling through the vast, dark emptiness of space. You are moving faster than any bullet ever fired, faster than any rocket ever launched. Right at this very moment, you are traveling at 1.3 million miles per hour. This is not science fiction. This is your reality. It is the speed of our entire solar system, our sun, our Earth, all of us, carried on an unimaginable journey through the cosmos. We feel nothing of this motion. We wake up, we drink our coffee, we live our lives, completely unaware of the tremendous velocity we possess. This incredible speed is not our own. We are passengers, adrift in a current far grander than any ocean. Our planet is caught in the gravitational pull of our sun. Our sun is caught in the immense gravitational embrace of our home galaxy, the Milky Way. It is a river of stars, gas, dust. We are but one tiny vessel swept along in its flow. The journey is silent. It is constant. It has been happening for every moment of your life and for every moment of human history. The ground beneath our feet feels solid and stable, a fixed point in the universe. But it is an illusion, a beautiful deception. We are, and have always been, cosmic travelers on an epic voyage. So, a question arises. Where are we going so fast? And what is this immense structure that carries us with such purpose? We look up at the night sky and see a faint, cloudy band of light. Our story begins long ago, in the deep, silent darkness of the early universe. Nearly 14 billion years have passed since the Big Bang. In the aftermath of that singular moment, the cosmos was a very different place. It was a hot, dense soup of particles and energy. There were no stars, there were no planets, and there were no galaxies. There was only a vast, expanding fog of hydrogen and helium gas, but it was not perfectly uniform. Tiny, almost imperceptible fluctuations in density existed within this primordial mist. These were the seeds of everything that was to come, planted in the first moments of time. Over millions of years, gravity began its slow, patient work. It is the great sculptor of the cosmos. The denser regions of gas began to pull in more and more material from their surroundings. They grew larger, more massive. These were the proto-galactic clouds, the ancestors of the galaxies we see today. Imagine countless wisps of cosmic smoke swirling and coalescing in the dark. Our own Milky Way began as one such collection of gas and mysterious dark matter. It was a formless entity, slowly but surely gathering the raw materials needed to build a city of stars. It was a promise of light in a universe that was still almost entirely dark. The first stars ignited within these collapsing clouds. They were giants, blue, brilliant, and living fast, violent lives. Much larger than our own sun, they burned through their fuel in only a few million years. When they died, they exploded in cataclysmic events called supernovae. These explosions were not just endings. They were also beginnings. They scattered heavy elements, forged in the hearts of these first stars, out into the surrounding gas. Carbon, oxygen, iron, the very elements needed for planets and for life, were seeded into the galaxy. Our galaxy was enriching itself, preparing the ground for future generations of stars, and eventually, for us. So what is this structure we call home? From the outside, our galaxy would look like a vast, spinning pinwheel of light. It is what astronomers call a barred spiral galaxy. At its heart is a dense, elongated bar of older, yellowish stars. This bar acts like a cosmic traffic director, funneling gas and dust from the outer regions toward the galactic center. It is a place of intense activity, a bright, bustling hub from which the rest of the galaxy extends. This central bulge is ancient, containing some of the first stars to ever form in the Milky Way. It is the Old City, the historic core of our stellar metropolis. Extending from this central bar are the magnificent spiral arms. These are not solid structures. They are more like cosmic traffic jams. They are density waves, ripples of higher gravity that sweep through the galactic disk. As gas clouds pass through these arms, they are compressed. This compression triggers furious bursts of star formation. This is why the arms are so bright. They are illuminated by the brilliant blue light of hot young stars. Our own sun resides in a smaller, partial arm called the Orion Spur, nestled between two larger arms, the Sagittarius arm, the Perseus arm. We live in a relatively quiet, suburban neighborhood of our galaxy. The main disk of the Milky Way, containing the spiral arms, is immense. It is about 100,000 light-years across. To put that in perspective, if our solar system were the size of a quarter, the Milky Way would be the size of North America. It is a flat, sprawling city of light, but it is also incredibly thin. While it is 100,000 light-years in diameter, the disk is only about 1,000 light-years thick. It is thinner, proportionally, than a vinyl record. All of this, the disk, the arms, and the central bar, are surrounded by a vast spherical halo of scattered old stars and ancient star clusters. And how many neighbors do we have in this city? The estimates are staggering. The Milky Way contains somewhere between 100 billion and 400 billion stars. For every single person who has ever lived on Earth, there are dozens of stars in our galaxy alone. And we are learning that many of these stars, perhaps most of them, have planets of their own. This opens up a profound possibility. With billions of stars and potentially trillions of planets, it seems almost inevitable that we are not alone. Our galaxy could be teeming with worlds, some like our own, some fantastically different, all part of this single, sprawling cosmic family. Our personal sense of time is defined by the Earth. A day is one rotation. A year is one orbit around the sun. But our sun has its own orbit, on a scale that dwarfs our human conceptions of time. Just as the Earth is gravitationally bound to the sun is bound to the supermassive black hole at the center of the Milky Way. Our entire solar system is on a grand circular tour of the galaxy. This journey is long. It takes our sun approximately 230 million years to complete a single orbit. This vast expanse of time is known as one galactic year. Think about what that means. The last time our solar system was in this same position in the galaxy, dinosaurs roamed the Earth. The continents were just beginning to drift into their current positions. The first mammals were small, nocturnal creatures, hiding from the great reptiles. Since that time, the dinosaurs have risen and fallen. The age of mammals has dawned. And in the last tiny fraction of this single galactic year, all of human civilization has emerged. Our recorded history is but a few seconds on this great cosmic clock. We have been alive for only a flicker of a galactic moment. Our journey is not a gentle one. As we orbit, we move up and down through the plane of the galaxy, like a horse on a carousel. We pass through regions of varying density. Sometimes we travel through the dense, bright spiral arms, where nearby supernovae could pose a risk. At other times, we are in the sparser regions between the arms, like we are now. Some scientists have even speculated that these passages through different galactic environments could have influenced life on Earth, perhaps triggering mass extinctions or periods of evolutionary change. Our fate is tied not just to our sun, but to the very geography of our galaxy. The center of our orbit is a place of profound mystery and power. At the very heart of the Milky Way, some 26,000 light-years away, lies Sagittarius A. It is a supermassive black hole, a point of infinite density with a gravitational pull so strong that nothing, not even light, can escape. It has a mass more than 4 million times that of our sun. Every star in the galaxy, including our own, is held in orbit by the combined gravity of all the other stars and, most importantly, by this unseen monster lurking in the core. It is the silent, invisible anchor around which our entire galaxy revolves. Yeah. When we look at our galaxy, we see stars, we see gas, we see dust, we see the visible matter. For a long time, we thought that was the whole story. But there was a problem. The galaxy is spinning too fast. The stars on the outer edges are moving with such velocity that they should fly off into intergalactic space. The gravity from all the visible matter we can see, even the hundreds of billions of stars, is not nearly enough to hold the galaxy together. It's like watching a merry-go-round spinning so fast that the children on the edge should be flung off, yet they remain firmly in place. There must be something else, something massive, yet completely invisible. Scientists call this missing ingredient dark matter. It does not emit light. It does not reflect light. It does not interact with forces we are familiar with, except for one: gravity. It is a cosmic ghost, a silent, unseen presence that outweighs all the visible matter in the universe by a factor of more than 5 to 1. We don't know what it is, but we know it is there. Its gravitational influence is the glue that holds our galaxy and all galaxies together. Without it, the beautiful spiral structures we see would have torn themselves apart long ago. The Milky Way's vast spherical halo extends far beyond the visible disk of stars and is thought to be composed primarily of this mysterious dark matter. It forms an invisible scaffolding, a gravitational framework upon which our galaxy was built. The gas and stars in the visible Milky Way are like the lights on a Christmas tree. The dark matter is the tree itself, unseen, providing the essential structure. This realization has fundamentally changed our understanding of the cosmos. About 85% of all matter in the universe is of a form we cannot see and do not yet understand. This mystery is one of the biggest challenges in modern physics. Our journey through the cosmos is not a solitary one. The Milky Way is part of a small cluster of galaxies called the Local Group, and we are on a collision course. Our nearest large galactic neighbor, the Andromeda Galaxy, is hurtling toward us at about 250,000 miles per hour. It is a cosmic spectacle, a gravitational dance that began billions of years ago. Right now, Andromeda is 2.5 million light-years away. But even at that immense distance, it is the most distant object you can see with the naked eye, a faint, fuzzy patch of light in the night sky. This is not a collision in the way we think of it on Earth. It will not be a crash of fire and destruction. Instead, it will be a slow, graceful merger. Because the distances between individual stars are so vast, direct collisions between stars will be exceedingly rare. It would be like two swarms of bees flying through each other. The swarms will merge, but very few individual bees will actually touch. Instead, the two galaxies will pass through one another, their shapes distorted by powerful gravitational tides. Stars will be flung out into long streams. The elegant spiral structures of both galaxies will be torn apart. This process will take hundreds of millions of years. After the first pass, the two galaxies will separate, only to be pulled back together again by their mutual gravity. They will dance and swirl, merging and reshaping each other over the eons. Eventually, after a long and complex gravitational tango, they will settle into a single, much larger galaxy. The gas from both galaxies will collide and collapse, triggering a spectacular burst of star formation, a galactic starburst that will light up the newly merged entity. Our night sky, for any observers who might exist then, will be a blaze of glory. The final result of this merger will be a new, giant elliptical galaxy. The beautiful spiral arms will be gone, replaced by a massive amorphous ball of older stars. Scientists have already given this future galaxy a name: Milkomeda. And what of our Sun and Earth? It is likely our solar system will survive. We will probably be thrown into a new, much larger orbit within this new galaxy. The collision is destined to happen in about 4.5 billion years. By that time, our Sun will be nearing the end of its life, swelling into a red giant. The fate of our galaxy is intertwined with the fate of our star, a future written in the laws of gravity. Well, that's the long view. We have journeyed across immense scales of space and time. From the dizzying speed of our solar system to the birth of our galaxy in the aftermath of the Big Bang. We have seen its structure, a city of stars 100,000 light-years across. We have contemplated the great galactic year, a 230 million year orbit that dwarfs human history. We have confronted the profound mystery of dark matter, the unseen scaffolding of the cosmos. And we have looked ahead to a distant future, to a cosmic collision that will reshape our galactic home. It is a story of unimaginable grandeur, enough to make one feel small and insignificant. But the final truth of this story is not one of separation. It is one of profound connection. Every piece of our world, every rock, every ocean, every living thing is intimately tied to the life and death of the stars in this galaxy. The first stars, those ancient giants, forged the heavy elements in their nuclear furnaces. When they exploded, they scattered these elements like seeds into the cosmos. Carbon, nitrogen, oxygen, iron, all the building blocks of planets, all the building blocks of life. Subsequent generations of stars, including our sun, formed from these enriched clouds of gas and dust. This means that the story of the galaxy is also our own personal origin story. The iron in your blood, which carries oxygen through your veins, was created in the heart of an exploding star billions of years ago. The calcium in your bones, which gives you structure and strength, was forged in the same cosmic crucible. The carbon that forms the basis of your DNA, the very blueprint of your existence, was once part of a distant, long-dead star. We are not just living in the Milky Way. The Milky Way is living in us. We are, in the most literal sense, stardust. So the next time you look up at the night sky at that faint milky band of light stretching across the heavens, remember what you are seeing. You are not just looking at a collection of distant suns. You are looking at your own ancestral home. You are looking at the source of the very atoms that make up your body. You are a child of the cosmos, a way for the universe to know itself. Every atom within you began its journey in a star, and has been traveling through this galaxy for billions of years, just to be here now as you. Well, simply incredible.
Imagine a universe where black holes are not merely cosmic endpoints, but dynamic engines of transformation. What if, instead of being silent, eternal voids, they could erupt in cataclysmic explosions, sending signals from the earliest epochs of the cosmos, encoded in bursts of energy that reach us across billions of years? Black holes are regions of space-time where gravity is so intense that the escape velocity exceeds the speed of light. They form from the gravitational collapse of massive stars, compressing matter into a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which no information can return. The event horizon is not a physical surface, but a mathematical demarcation in the fabric of space-time. For much of the 20th century, black holes were considered perfect one-way traps. Nothing, not even light or information, could escape their grasp. This view changed dramatically in the 1970s when Stephen Hawking applied quantum field theory to curved space-time, revealing that black holes are not entirely black but emit radiation due to quantum effects near the event horizon. Hawking radiation arises from quantum fluctuations at the event horizon, where particle-antiparticle pairs spontaneously form. Occasionally, one particle falls into the black hole while the other escapes, resulting in a net loss of mass and energy. Over astronomical timescales, this process leads to black hole evaporation, a profound intersection of general relativity, quantum mechanics, and thermodynamics. For stellar mass black holes, this evaporation is unimaginably slow, far exceeding the current age of the universe. A solar mass black hole would take approximately 10 circumflex 67 years to evaporate completely. However, the rate of Hawking radiation increases as the black hole shrinks, leading to a runaway process in the final stages. This raises a fascinating question. What if there exist much smaller black holes formed in the early universe? Enter primordial black holes, hypothetical remnants from the high-density fluctuations in the first fractions of a second after the Big Bang. Unlike stellar black holes, these could range in mass from that of a mountain to less than a gram, yet possess immense gravitational fields. Their existence is still theoretical, but they offer a unique window into the physics of the early universe and the nature of dark matter. Unlike their massive counterparts, primordial black holes with sufficiently low mass could have been evaporating via Hawking radiation for billions of years. Some may be reaching the end of their lifespans right now, culminating in a final energetic outburst, a phenomenon that could be observable as a brief, intense flash of high-energy radiation. The terminal phase of black hole evaporation is predicted to be a violent explosion, releasing a burst of gamma rays and energetic particles. This process, though never observed, is a subject of intense theoretical and experimental interest. Detecting such an event would provide direct evidence for Hawking radiation and offer insights into quantum gravity. Astrophysicists are actively searching for these transient signals, short-lived gamma-ray bursts or unexplained flashes in the cosmic microwave background that could signify the final moments of primordial black holes. Such detections would not only confirm a key prediction of quantum field theory, but also illuminate the conditions of the early universe. The implications are profound. Some models propose that primordial black holes could constitute a significant fraction of dark matter, the invisible mass that shapes galaxies and cosmic structure. If even a single evaporating black hole is detected, it could revolutionize our understanding of cosmology and the fundamental constituents of the universe. Others suggest that the study of black hole explosions could reveal new physics, perhaps unifying general relativity and quantum mechanics, or exposing phenomena beyond the standard model. The interplay between gravity, quantum fields, and space-time curvature remains one of the deepest mysteries in theoretical physics. Picture a solitary flash of light in the night sky, a message encoded in energy carrying information from the universe's infancy. Each such event would be a cosmic relic, a direct probe of conditions mere moments after the Big Bang, and a testament to the unity of the laws of nature across time and space. Should an evaporating black hole be observed in our era, it would be more than a scientific milestone. It would be a message from the origin of everything, a fleeting glimpse into the universe's primordial state, and a key to unlocking its most profound secrets. So as you gaze into the night sky, remember, the cosmos is a vast laboratory, filled with enigmas awaiting discovery. Somewhere, perhaps even now, a black hole may be preparing its final brilliant transmission, a cosmic signal challenging us to decipher the ultimate laws of reality.
What if I told you that everything you know is a lie? The world around you, the chair you're sitting on, the air you breathe, the stars twinkling in the night sky are not quite real. Imagine that this entire universe is nothing more than an elaborate computer simulation. It's like science fiction. You might dismiss it. But what if clues are hidden all around us, embedded in space and time? What if the laws of physics are actually code? This isn't just late-night musing. It has fascinated brilliant minds. We think of reality as tangible. We trust our senses. We believe what we see, touch, and feel. Our senses are easy to fool. Optical illusions, dreams, virtual reality all show how convincing a fabrication can be. How can we be certain this is the genuine article? Are we characters in someone else's advanced video game, living out a pre-programmed life? The proposition is staggering. It forces us to question our basic assumption. One true reality. If it isn't, then every discovery, every historical event, every personal memory could be part of a script. The feeling of the sun on your skin might be simulated heat. It's a dizzying idea. It can make you question your sanity. But science pursues unsettling ideas. Those questions lead to breakthroughs. We look outward to the cosmos, distant galaxies, exploding stars. Maybe the biggest revelation is inward, the nature of existence itself. Are we biological beings evolved on a rocky planet, or informational constructs running on a cosmic supercomputer? We are on the verge of a paradigm shift, a leap of faith like Neo, and choose which pill we want to swallow. The idea that our reality might be an artificial construct found its modern voice through a philosopher named Nick Bostrom. In 2003, he published a paper that laid out a compelling argument. Not a wild guess, but a logical exercise. Bostrom proposed one of three possibilities must be true. First, civilizations like ours almost always go extinct before they can develop hyper-realistic simulations. Second, advanced civilizations lose interest in creating such simulations. Third, we are almost certainly living inside a computer simulation right now. Think about it. If civilizations can create simulated worlds, they would likely create many of them. This idea has deep roots in philosophy and decades of science fiction. The Matrix brought the idea to the masses. Tron showed programmers digitized inside their creations. Ready Player One imagines a society living inside a vast, shared virtual universe. These stories act as thought experiments about technology and ethics. Bostrom's argument hinges on projecting our technological trajectory. We went from Pong to sprawling photorealistic open worlds. Now, imagine projecting that progress forward thousands or millions of years. An advanced civilization could create simulations indistinguishable from base reality. The beings inside wouldn't know. They'd think their world is real. Why run ancestor simulations? For scientific research, to study societies, for entertainment, the ultimate immersive experience, or for reasons beyond our comprehension. The key takeaway is statistical. Countless simulated universes for every one base reality. The odds then favor us being in a simulation. It's a sobering thought. We might be a copy of a copy, living inside someone else's experiment. How could a universe as vast and complex as ours possibly be just information? The answer may lie in one of the strangest and most successful theories in all of science: quantum mechanics. On the cosmic scale of planets and galaxies, the universe seems to follow predictable rules, the classical physics of Newton-Einstein. But when we zoom in, way down to the subatomic level, electrons, photons, the rules change completely. Here, in the quantum realm, things don't have definite properties until we measure them. An electron doesn't have a specific position. Instead, it exists in a cloud of probabilities, a wave of potential locations. This is where things get truly bizarre. The very act of observing a quantum particle seems to force it to choose a state. Before you look, it's everywhere and nowhere at once. When you measure it, its probability wave collapses, and it snaps into a single, definite location. This observer effect is one of the deepest mysteries in physics. It suggests that reality, at its most fundamental level, isn't a solid, pre-existing thing. Instead, it seems to be something that is brought into being through the act of observation or interaction. It's as if the universe is waiting for a conscious observer to render the details on demand. This strange behavior has led some physicists to consider a radical idea known as digital physics. This school of thought proposes that the universe isn't just described by information, but that it is, in its essence, information. Every particle, every force, every law of physics could be the output of a computational process. The universe, in this view, is like a giant computer. Space, time are not smooth and continuous, but are made of tiny, discrete units like pixels on a screen. If you could zoom in far enough, you might find the fundamental resolution of the universe, a smallest possible length known as the Planck length. If reality is made of these discrete units, it would mean that the universe has a finite amount of information it can contain. The bizarre rules of quantum mechanics and the apparent pixelation of space-time might not be mysteries at all. They could be the telltale signs of the underlying code. The legendary physicist John Archibald Wheeler summed up this entire line of thinking with a simple, elegant phrase: it from bit. So what did he mean by that? He was proposing a revolutionary new way of looking at the universe. The it represents everything in the physical world, every particle, every planet, every galaxy. It's all the tangible stuff we call reality. The bit is the fundamental unit of information. A yes or no answer, a 1 or a 0. Wheeler's idea: every it derives existence from bits processed at the deepest level. Think of it like a character in a video game. That character appears solid on screen. It can run, jump, interact with the environment, but at its core, it's not flesh and blood. It's bits of information. Its look, abilities, and rules come from the game's code. Wheeler suggested the universe might work the same way. An electron isn't a tiny solid ball. It's the result of yes or no questions being answered. Is it here? Is it spin up? Those binary answers, bits, conjure the electron. This changes how we view physics. Laws like gravity, electromagnetism might not be fundamental. They could be algorithms, computational rules the cosmic computer follows. So discovering a law may be reverse engineering source code. Physicists become cosmic hackers decoding the programming language of existence. If true, information is more fundamental than matter and energy. Before the Big Bang, maybe a sea of pure information, a blank computational slate. The Big Bang could be the moment the program was run, when bits started processing intuits. Our cosmos could be the output of a colossal computation. We are living in the output of a cosmic information processor. As you might imagine, not everyone in the scientific community is ready to embrace the simulation hypothesis. For many physicists, the idea, while fascinating, straddles a dangerous line between science and pure philosophical speculation. A core principle of the scientific method is that a hypothesis must be testable. It has to make predictions we can verify or falsify through experiment. Critics argue the hypothesis may be fundamentally untestable. How could we design an experiment to prove we are or are not inside a simulation? The arguments against it are compelling. Physicist Lisa Randall, for example, has expressed skepticism, saying the odds are effectively zero. She and other critics say the case relies on many assumptions about how future civilizations would behave and what their motivations might be. We project our own desires for gaming and for research onto hypothetical, super-advanced beings. It's a very human-centric view. Who's to say they wouldn't find ancestor simulations boring, unethical, or a complete waste of computational resources? Some argue clues like the pixelation of space-time at the Planck length or the observer effect in quantum mechanics are not evidence of a simulation. They might just be fundamental features we don't yet understand. Attributing them to a simulation is a God of the gaps move. Where we have gaps, we insert a simulator. It's an easy answer, but may not be the right one. Science fills gaps with evidence and theory, not an unknowable programmer. Still, proponents search for tests. Some scientists propose looking for glitches, small inconsistencies in physical laws that might reveal a computational substrate. For example, high-energy cosmic rays might behave slightly differently if they're bumping against a simulated space-time grid. So far, no such evidence has been found. The simulation idea is tantalizing and mind-bending, but for now it sits at the edge of scientific inquiry, waiting for a test that could confirm our wildest digital dreams or bring us back to solid, unsimulated ground. If we do live in a simulation, the implications are truly mind-boggling. Let's start with the idea of glitches in the matrix. In any complex computer program, bugs are inevitable. No matter how sophisticated the code, errors can occur. In our reality, a glitch might not look like a cat repeating its actions. It might manifest as a subtle violation of the laws of physics, a momentary flicker in a physical constant, or a particle appearing where it really shouldn't be. Events like déjà vu or unexplained phenomena, often dismissed as tricks of the mind, take on a whole new meaning. Could they be the system momentarily lagging, or maybe an error in the code of our world? The idea also opens the door to the concept of nested simulations, kind of like a set of Russian dolls. If an advanced civilization can create a realistic simulation, what's to stop the simulated beings inside from eventually developing their own technology to create their own simulations? This could lead to a potentially infinite hierarchy of realities, each one a simulation created by the civilization in the level above it. We could be living in a simulation within a simulation within a simulation, and so on. Where does it end? Is there a base reality at the very top, or is it simulations all the way down? This leads to another profound question. What about our creators? If we are simulated beings, then we were created by a higher intelligence. This doesn't necessarily mean a divine being in the religious sense, but rather a civilization of programmers, engineers, or maybe even a bored teenager in a higher dimension. This civilization would be, for all intents and purposes, our gods. They would have the power to alter the laws of physics, rewind time, or even shut down the simulation entirely. The thought that our entire existence could be terminated with a single keystroke, the ultimate Ctrl-Alt-Delete, is both terrifying and humbling. And so we arrive at the ultimate question, the one that lingers long after the scientific debates have quieted. If our universe is a simulation, a grand piece of cosmic code, then who or what wrote it? Who is the programmer? This question takes us beyond the realm of physics and into metaphysics and philosophy. Are our creators biological beings like us, just far more advanced? Or are they post-biological artificial intelligences beyond physical bodies? The possibilities are limitless. Maybe the simulation wasn't even intentional. Maybe it's a byproduct, a student science fair in a higher dimension. Imagine a young being running a galaxy formation simulation. Conscious life spontaneously emerges. To them, we're an unexpected data point. The purpose of our existence could be accidental. The meaning we search for in art, in science, in religion, an emergent property of someone else's program. This forces us to confront our cosmic significance. For millennia, we've put ourselves at the center. Physically, then philosophically. The simulation hypothesis is the ultimate demotion. It suggests we may not be part of the real universe. But does that diminish our lives? Does it make love any less meaningful? Joy any less meaningful? Discovery any less meaningful? The experiences are real to us, the pain we feel is real, the beauty of a sunset is real. Even if it's rendered pixels, our awe is genuine. We're left staring into the great unknown. Whether base reality or simulation, the quest for understanding gives our existence meaning. The search for the programmer is a noble, profound purpose, and who knows what you might find.
We've all seen it. The desperate command from the cockpit of a starship. A Corellian freighter, perhaps. The frantic flip of a switch, the pull of a lever. Stars, once distant points of light, stretch into brilliant streaks. The ship lurches with a flash. It vanishes into a swirling tunnel of pure energy. This is the jump to hyperspace, a cornerstone of science fiction, the promise of crossing unimaginable distances in the blink of an eye, making a vast, sprawling galaxy feel like a neighborhood. It allows heroes to outrun empires and explorers to chart unknown worlds. A beautiful, thrilling, utterly captivating idea, the dream of faster-than-light travel, breaking free from the cosmic chains that bind us to our solar system. In cinematic moments, the laws of physics seem to melt away. A simple calculation, a quick repair to the hyperdrive motivator, the journey from a desert planet to a forest moon takes mere hours, not millennia. In 1905, a young patent clerk named Albert Einstein published a series of papers that would forever change our view of the universe. He gave us a new framework for understanding reality, a theory known as special relativity. And within that theory, he revealed a fundamental rule of the cosmos, a kind of universal speed limit. This cosmic speed limit is the speed of light in a vacuum, a staggering 299,792 kilometers per second, or about 186,282 miles per second. It's a number we often abbreviate with the letter CE. Nothing with mass, Einstein showed, can ever reach this speed, let alone surpass it. Think about it. Light from the sun takes a little over 8 minutes to reach Earth. A beam of light could circle our planet more than 7 times in a single second. It is an almost incomprehensible velocity. Yet, according to Einstein, this is the ultimate speed. It's not a technological barrier that we can one day engineer our way past. Like the sound barrier, it is woven into the very fabric of space-time itself. It's a law of nature as fundamental as gravity. This one simple, elegant idea acts as the great gatekeeper of the cosmos, dictating where we can go and how fast we can get there. This concept stands in stark opposition to the world of Star Wars, where the Millennium Falcon zips from Tatooine to Alderaan in what seems like no time at all. Einstein's theory of relativity doesn't just set a speed limit, it explains why that limit exists. And the reason is one of the most famous equations in all of science, E equals mc squared. This equation tells us that energy mass are two sides of the same coin. They are convertible. You can turn mass into a tremendous amount of energy. Nuclear power plants, stars. But it also works the other way around. Energy can, in a sense, become mass. And this is the crux of our problem. As you accelerate an object, you are constantly pumping kinetic energy into it. According to relativity, that added energy contributes to the object's total mass. So the faster you go, the more massive you become. At everyday speeds, this increase in mass is so infinitesimally small that we can't even detect it. But as you start to approach the speed of light, the effect becomes dramatic. A spaceship traveling at 87% the speed of light would have twice its resting mass. At 99.5% the speed of light, it would be 10 times more massive. If Einstein's laws prevent us from moving through space faster than light, what if we could, move space itself? This is the brilliant and highly speculative idea behind the Alcubierre warp drive, a theoretical concept proposed by physicist Miguel Alcubierre back in 1994. The idea doesn't break the law of special relativity. Instead, it kind of cleverly exploits a loophole in Einstein's other great theory, general relativity. General relativity tells us that massive objects can bend and warp the fabric of space-time. This is what we experience as gravity. The Alcubierre drive suggests we could actually do this on purpose. Imagine your starship is sitting inside a bubble of normal, flat space-time. The drive would work by contracting the space-time in front of the bubble and at the same time expanding the space-time behind it. The ship itself isn't moving through space in the traditional sense. It's more like a surfer riding a wave on the fabric of reality. The space in front of you shrinks, and the space behind you grows, pushing your bubble forward. From inside the bubble, you would feel no acceleration at all. You could be perfectly still, sipping your coffee while your bubble zips across the galaxy at an effective speed many times greater than light. If bending space in a wave is too difficult, what about, well, punching a hole through it? This leads us to another fascinating concept from Einstein's general relativity, the wormhole, or as it was originally called, an Einstein-Rosen bridge. A wormhole is a theoretical tunnel, a shortcut through the fabric of space-time. Imagine space-time is a giant sheet of paper. To get from one point on the paper to another, you would normally have to travel across its surface. But what if you could fold the paper over, bringing the 2 points very close together, and then poke a pencil through both layers? That pencil hole is the wormhole. This shortcut wouldn't require you to travel faster than light. You would enter one mouth of the wormhole and emerge from the other mouth, located somewhere else in the universe, almost instantaneously. The journey through the tunnel could be very short, even if the two mouths are separated by millions of light years in normal space. This method, like the Alcubierre drive, circumvents the cosmic speed limit. However, according to our current understanding, naturally occurring wormholes, if they exist at all, would likely be microscopic on the scale of subatomic particles. Even if you found one, it would be unstable. It would snap shut in an instant, likely before even a single photon of light could make it all the way through. Let's compare these wild theoretical ideas to what we see in our favorite space sagas. When Han Solo boasts that the Millennium Falcon made the Kessel Run in less than 12 parsecs, he's famously, maybe even intentionally, confusing a unit of distance with a unit of time. But the implication is clear. The ship's powerful hyperdrive allowed it to take a dangerous shortcut. This sounds a lot more like a wormhole than an Alcubierre drive. The ship didn't just point itself at its destination and travel in a straight line. It navigated a specific treacherous route through an alternate dimension or a series of space-time tunnels. In the Star Wars universe, hyperspace is often treated as a parallel dimension that coexists with our own. Ships enter it, travel for a while, and then re-emerge in normal space. This requires a hyperdrive and a navicomputer. A navicomputer calculates a safe route, avoiding mass shadows of stars and planets. Those mass shadows could pull a ship out of hyperspace with catastrophic results. This separate dimension idea is a convenient narrative device, but it has no direct analog in modern physics. So, where does this leave us? Are we forever trapped in our cosmic neighborhood, destined only to gaze at the stars through telescopes? It is easy to look at the challenges, the infinite energy, the need for exotic matter, and conclude that faster than light travel is simply impossible. And based on everything we know today, in the year 2025, that is the most rational conclusion. The laws of physics, as we currently understand them, have posted a clear no trespassing sign at the speed of light. But science is a story of overturned conclusions. A few centuries ago, the most brilliant minds would have told you that flying was impossible for humans, that splitting the atom was a fantasy, and that traveling to the moon was the stuff of madmen. Our understanding of the universe is a work in progress. We are still uncovering the deepest secrets of reality. Concepts like dark matter and dark energy show us that the vast majority of the universe is made of stuff we don't understand at all. Who is to say that within these great cosmic mysteries, we won't find something that changes the game entirely? Perhaps exotic matter is not impossible, just rare. Perhaps a future breakthrough in quantum physics or our understanding of gravity will reveal a new way to manipulate space-time. The theories of Alcubierre and Einstein-Rosen bridges are our first tentative steps into a much larger intellectual world. They are the equivalent of early drawings of flying machines with flapping wings. They might be wrong in their details, but they point us in a direction. The human spirit is defined by its refusal to accept limits. We are explorers by nature. We look at the vast, dark ocean of space not as an impassable barrier, but as the next frontier. The stars are waiting.
Why does the universe, our grand cosmic home, seem to play by two entirely different sets of rules? On a scale we can see and touch, everything appears orderly, predictable, and reassuringly solid. Planets follow their ancient, graceful paths around stars. A ball thrown into the air traces a perfect arc, its path sealed by gravity the moment it leaves your hand. A magnificent clockwork of cause and effect, gears turning in harmony. It's the world of classical mechanics, the physics that built our civilization and sent us toward the stars. but shrink your perspective. Journey down, 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 mountains, cities, a single grain of sand, beyond cells past molecules into the realm of the atom. Here, the rules dissolve into a bewildering carnival of strangeness. Particles become shimmering clouds of probability. They can exist in multiple places at once. They can be neither here nor there, but both until you look. This is quantum mechanics, as real as orbiting planets. Two frameworks: classical mechanics, quantum mechanics, twin pillars. Two languages describing one universe, sounding alien to each other. One promises certainty, a cosmos written in the stars. The other speaks of uncertainty, chance, and probability, observation shaping reality. How can both be true? How does solidity arise from probabilistic waves? From Newton's apple to Einstein's thought experiments to Bohr, we confront the limits of intuition and accept a stranger, more wonderful universe. We live on the seam between two realities, a bridge between clockwork and chaos. Explore both sides. Embrace the harmony of the large, the magic of the small. Let's begin in a world that feels like home. The world of classical mechanics. This is the physics of our everyday lives. A child spinning top the majestic sweep of galaxies. Its story is largely the story of one monumental genius, Sir Isaac Newton. In the 17th century, Newton gave us simple, elegant laws of motion and a universal law of gravitation. These laws were revolutionary. The same force that pulls an apple from a tree also holds the moon in orbit around Earth. The heavens and the earth were united under one set of rules. Newton's laws rest on determinism. If you know the position and momentum of every object and all the forces on them, you could predict the future with perfect accuracy. Imagine the universe as a colossal game of billiards. Exact starting position, exact speed, exact direction, and you could calculate every collision from break to pocket. In this view, the universe is a machine. Vast, intricate, and knowable, its future written in its present. These laws are the bedrock of technology. When engineers design a bridge, they calculate tension and compression, ensuring it withstands traffic and wind. When we launch a rocket to Mars, it's not guesswork. It's precise celestial calculation, plotting trajectories through the Sun, Earth, and Mars. Your phone's GPS uses the same principles, tracking you relative to satellites. This classical world feels certain. Objects have definite properties. A car has a specific location and speed. It cannot be in two places at once. Its path is continuous and smooth. Energy and momentum are conserved, transferred but never lost. This conservation brings order. It lets a pendulum swing and governs galactic collisions. For centuries, we believed this was the whole story. We thought we'd found the universe's operating manual. But we were only reading the first chapter. As the 19th century gave way to the 20th, cracks began to appear in the perfect facade of classical physics. Scientists studying phenomena like the light emitted by hot objects and the nature of the electron found that the old rules simply didn't work. The universe, it turned out, had a secret life. To explain these puzzling observations, a new theory was born, quantum mechanics, and with it, our understanding of reality was turned upside down. The solid, predictable world of Newton was replaced by a fuzzy, probabilistic landscape. One of the first bizarre discoveries was wave-particle duality. In the classical world, things are either particles, like a baseball, or waves, like a ripple in a pond. But in the quantum realm, entities like electrons and photons of light behave as both. Depending on how you measure it, an electron can act like a localized particle, or like a spread-out, undulating wave. It's not one or the other, it's both. This duality is a fundamental property of matter. Then, superposition. A quantum particle can exist in a combination of all possible states simultaneously. Imagine a coin spinning in the air. Classically, it will land heads or tails. A quantum coin can be both heads and tails at the same time. It's a ghostly blend until a measurement is made. Measurement forces the particle to choose. Wave function collapse. Your observation helps create the reality you see. And it gets even stranger. The uncertainty principle, from Werner Heisenberg, limits what we can know. You cannot know both position and momentum exactly. Measure position precisely, and momentum becomes uncertain, and vice versa. This is a built-in fuzziness of the universe. Finally, entanglement. Two entangled particles link so measuring one instantly influences the other, no matter the distance, across a room or across the galaxy. The journey into the quantum realm was not the work of a single mind like Newton's, but a collaborative, often contentious effort by a generation of brilliant physicists. They were explorers charting territory so strange, it defied language and intuition. Max Planck took the first steps in 1900. While studying blackbody radiation, he proposed energy came in discrete packets, quanta. He thought it a trick, but he'd planted a revolutionary seed. A few years later, a young Albert Einstein took that seed he used like quanta, photons, to explain the photoelectric effect. That work earned him the Nobel Prize. The 1920s became the heroic age of quantum mechanics. A cohort of daring young thinkers built its mathematical and conceptual framework. Niels Bohr developed an atom model with quantized energy levels explaining why atoms emit light at specific frequencies. Louis de Broglie proposed that all matter, not just light, has a wave-like nature seen in electron diffraction patterns. Erwin Schrödinger formulated a wave equation describing how quantum states evolve over time, the quantum analog of Newton's laws. Werner Heisenberg developed matrix mechanics and introduced the uncertainty principle, linking observer and observed. These scientists, and others like Wolfgang Polymax Born, wrestled with mathematics and deep philosophical implications. What did it mean for reality to be probabilistic? What was the role of the observer? The debates were legendary, most famously Einstein versus Bohr. Einstein: God does not play dice. He argued quantum mechanics was incomplete, pointing to hidden variables. Bohr replied, stop telling God what to do. Their debate forced physicists to confront the nature of reality, a conversation still ongoing. These architects of the impossible didn't just discover new rules, they gave us a new universe. While the principles of quantum mechanics might sound like abstract philosophy or science fiction, they are not confined to dusty blackboards, distant laboratories. The bizarre behavior of particles in the subatomic realm is the engine driving much of the technology that defines our modern world. You are experiencing the practical results of quantum mechanics right now. The device you are using to read this essay, a computer, a tablet, a smartphone, is a quantum machine. Its heart is a microchip filled with billions of transistors, semiconductor devices governed by the quantum behavior of electrons. Without our understanding of how electrons move through materials like silicon, transistors would be impossible. Classical physics predicts that electrons shouldn't be able to do what they do inside a chip. Quantum mechanics, specifically the theory of energy bands in solids, explains it perfectly. This understanding allows us to control the flow of electricity at an incredibly small scale, creating the binary language of ones and zeros that forms the basis of all digital information. Every time you save a file, stream a video, or send a message, you are relying on the predictable application of quantum weirdness. Look around you. The laser is another quintessential quantum invention. The word laser is an acronym for light amplification by stimulated emission of radiation. The key concept, stimulated emission, was first proposed by Einstein. One photon can trigger an atom to release a second identical photon. Contained in a mirrored cavity, this makes a cascade, a coherent focused beam. Lasers are everywhere. In barcode scanners at the grocery store, in Blu-ray players, in fiber optic cables that carry the internet across oceans, in delicate surgical procedures. The influence of quantum mechanics extends even into our hospitals. Magnetic resonance imaging, or MRI machines, produce detailed images of soft tissue through nuclear magnetic resonance. A powerful magnetic field aligns the quantum spin of protons in the water molecules of your body. A radio wave knocks them out of alignment, and the machine listens for the signals they emit as they return. By analyzing these signals, a computer constructs a detailed three-dimensional map of your internal anatomy, all without any harmful radiation. From computing to communication to medicine, the quantum world is not a distant, strange land. It's the invisible foundation of our 21st century lives. So we have these two magnificent theories, classical mechanics, quantum mechanics. Both are incredibly successful within their own domains. But how do they stack up side by side? The most obvious difference is scale. If the universe is fundamentally quantum, built on a foundation of uncertainty and probability, then where does the solid, predictable classical world come from? The answer lies in a crucial concept known as the correspondence principle, first articulated by Niels Bohr. This principle states that the predictions of quantum mechanics must agree with the predictions of classical mechanics in the limit of large systems. As you scale up from the atomic to the everyday, the weirdness of quantum mechanics should fade away, leaving the familiar certainty of Newton's laws. This transition happens through a process called quantum decoherence. A quantum object, like a single electron, can maintain its strange superposition state as long as it is perfectly isolated from its environment. But in the real world, perfect isolation is impossible. A macroscopic object, a dust mote, a baseball U, is constantly interacting with its surroundings. Trillions upon trillions of air molecules, photons of light, and cosmic rays are bombarding it every microsecond. Each of these tiny interactions acts as a measurement, observing the object's position and forcing its quantum wave function to collapse. And what emerges is a single loud classical shout.
What happens when a star, after burning for millions or billions of years, finally runs out of fuel? This is not just a question about a distant point of light. It is a question about the very engine of cosmic creation and destruction. The stars that illuminate our night sky are not eternal flames. They are vast, dynamic nuclear reactors, engaged in a constant, delicate balancing act. Gravity relentlessly pulls their immense mass inward, seeking to crush them into oblivion. At the same time, the nuclear fusion in their cores generates tremendous energy, pushing outward and holding that collapse at bay. For most of a star's life, these two forces are in perfect equilibrium, a cosmic stalemate that allows the star to shine steadily for an almost unimaginable length of time. But this balance cannot last forever. The hydrogen fuel that powers a star's core is a finite resource. When it begins to run low, the outward push from fusion weakens, and gravity starts to gain the upper hand. The star enters its final dramatic chapters. Instead, the death of a star is one of the most spectacular and transformative events in the entire universe. The path it takes depends critically on one single factor: its mass. The answer is a story of immense power, profound change, and incredible beauty. The first major stage in a star's demise begins when the hydrogen fuel in its core is depleted. For its entire main sequence life, the star has been fusing hydrogen atoms into helium. But when that core hydrogen runs out, the fusion furnace sputters and goes out. Without the outward pressure from fusion, the core begins to collapse under its own immense weight. As it collapses, it heats up dramatically, becoming far hotter than it ever was. This intense heat ignites a shell of hydrogen fusion in the layers just outside the core. This surge of energy pushes the star's outer layers outward with irresistible force. The star begins to swell to an enormous size, growing hundreds or even thousands of times larger. As the surface expands, its energy is spread over a much larger area, causing the surface temperature to drop. The star's color shifts from a brilliant white or yellow to a deep, ominous red. The star has now become a red giant. In approximately 5 billion years, our sun will begin its transformation into a red giant. Its expansion will be so vast that it will swallow the orbit of Mercury completely, Venus completely. It may even expand far enough to engulf Earth itself, boiling away our oceans. During this phase, the sun will also begin to lose mass, shedding its outer layers in a powerful stellar wind. For low and medium mass stars, including stars like our sun, the end of their life is a process of serene dissipation rather than violent explosion. Once the star has exhausted its helium fuel in the core, its nuclear furnace shuts down for good. It simply does not have enough mass and therefore not enough gravitational pressure. In a series of thermal pulses, it begins to gently puff away its outer layers. These expelled layers of gas, enriched with elements like carbon and oxygen, expand outward in a beautiful glowing shell. This expanding cloud is illuminated by the intense ultraviolet radiation streaming from the hot, exposed core left behind. The result is one of the most beautiful objects in the cosmos, a planetary nebula. At the heart of every planetary nebula lies the remnant of the star's core, a white dwarf. A typical white dwarf might contain about half the mass of our sun, but compressed into a volume roughly the size of Earth. A single spoonful of white dwarf material would weigh several tons on Earth. This extreme density is the result of a quantum mechanical phenomenon known as electron degeneracy pressure. A newly formed white dwarf is incredibly hot, with surface temperatures exceeding 100,000 degrees. However, with no internal source of energy, it is essentially a dying ember. Over billions of years, it will gradually cool and dim, its color shifting from white to yellow to red. Eventually, it will cool completely and become a cold, dark ball of carbon and oxygen, a black dwarf. In that quiet ending, the echoes of their lives continue to shape everything we know. The lives of massive stars are dramatically shorter and more violent than those of their smaller cousins. They burn through their fuel at a ferocious rate, living fast and dying young. As they age, they build up a core of iron, the ultimate ash of nuclear fusion. Unlike lighter elements, fusing iron atoms together consumes energy rather than releasing it. The outward pressure that had supported the star for millions of years vanishes in an instant. Gravity, the relentless force that has been trying to crush the star its entire life, finally wins. In less than a second, the iron core catastrophically collapses inward at incredible speeds, reaching up to a quarter of the speed of light. The infalling outer layers slam into this newly formed super-dense object and rebound. The shock wave is supercharged with energy from a flood of ghostly particles called neutrinos. This explosive rebound is a Type II supernova, one of the most energetic events in the universe. In the moments of this explosion, the star briefly becomes as luminous as an entire galaxy of hundreds of billions of stars. The extreme conditions trigger nuclear reactions that create all elements heavier than iron. Gold, silver, platinum, uranium, every atom of these elements was forged in a supernova explosion. The star scatters these newly forged heavy elements across the galaxy. This expanding cloud of debris will cool and mix with surrounding gas and dust. These remnants are not just relics, they are seeds that will enrich the next generation of stars, planets, and perhaps even life. If the core's mass is between approximately 1.4 and 3 times the mass of our Sun, a truly extraordinary object is formed, a neutron star. The pressure is so intense that it forces electrons and protons to merge, forming neutrons. The entire core becomes a single gigantic atomic nucleus composed almost entirely of neutrons. A neutron star contains more mass than our Sun, yet compressed into a sphere only about 20 kilometers in diameter, roughly the size of Manhattan. A single sugar cube's worth of neutron star material would have a mass of about 100 million tons. Its surface gravity is hundreds of billions of times stronger than Earth's. The neutron star spins at incredible speeds, often rotating hundreds of times per second. This rapid rotation concentrates the original star's magnetic field, making it trillions of times stronger than Earth's. This intense magnetic field generates powerful beams of radiation that shoot out from the neutron star's magnetic poles. Because the magnetic poles are not aligned with the rotational axis, these beams sweep across the cosmos like a lighthouse. If one of these beams sweeps across Earth, our radio telescopes detect a regular pulse of energy. These rapidly spinning, beaming neutron stars are known as pulsars. The regularity of their pulses is so precise that they are among the most accurate clocks in the universe. Neutron stars are extreme laboratories for physics, pushing matter to its absolute limits. The discovery of pulsars in 1967 was a landmark moment, providing first evidence for neutron stars. They remain among the most fascinating objects in the cosmos, the city-sized cinders left behind by the universe's greatest fireworks. If the remnant core weighs more than about 3 times the mass of our Sun, then not even the immense pressure of packed neutrons can withstand gravity. There is no known force in the universe that can halt the collapse. The core is compressed into an infinitely dense, zero-volume point, a singularity. This singularity is surrounded by a region of space-time so warped that it becomes a one-way street. An object has been created from which nothing, not even light itself, can escape, a black hole. The boundary of this region is called the event horizon, not a physical surface, but a theoretical border. Once anything crosses the event horizon, it can never communicate with the outside universe again. We cannot see a black hole directly. Instead, we watch as stars orbit a patch of empty space at incredible speeds. Matter forms a rapidly rotating accretion disk, heated to millions of degrees by friction. This causes the disk to glow brightly in high-energy wavelengths like X-rays. Powerful magnetic fields can channel matter into colossal jets blasted away at nearly the speed of light. These jets can extend far beyond their host galaxy. At the center of nearly every large galaxy lurks a supermassive black hole with mass millions or billions of times that of our Sun. These behemoths play a crucial role in galaxy evolution, regulating star formation throughout the galaxy. Black holes are fundamental architects of the universe. The death of the most massive stars is intimately linked to the life and growth of the largest structures in the cosmos. The death of a star, whether gentle, fading, or violent explosion, is never truly an end. It is a transformation. When a low-mass star sheds its layers, it enriches space with lighter elements like carbon and nitrogen. When a massive star explodes, It forges and flings heavier elements throughout the galaxy. The oxygen we breathe, the iron in our blood, the silicon in rocks, all were forged in stellar furnaces. We are made of star stuff. The history of the universe is written in our own biology. Looking up at the night sky is like looking back at our own cosmic family tree. The faint light from distant stars and nebulae tells the story of our origins. Our own sun will follow this path in the distant future. In about 5 billion years, it will swell into a red giant. It will shed its layers as a planetary nebula and leave behind a cooling white dwarf. Life on Earth will not survive this transformation, but the atoms that make up our planet will be returned to the cosmos to become part of new stars, planets, and perhaps new life. The death of a star is not an ending to be feared, but a process of renewal to be understood. It is the mechanism by which the universe endlessly reinvents itself, ensuring that even in darkness and destruction, there are always the seeds of new beginnings. Even our own sun will one day die, becoming a white dwarf, but not for another 5 billion years. Until then, we continue to be part of this magnificent cosmic story, children of the stars, witnesses to the universe's endless capacity for renewal and wonder.
What if the universe doesn't follow the rules we see every day? Have you ever truly looked at your hand and wondered what it's made of? Or gazed at the stars and questioned the fundamental nature of the reality we inhabit? For centuries, we thought we had the answers. The universe, according to classical physics, the physics of Isaac Newton, was a grand, predictable machine, a cosmic clockwork where planets followed perfect orbits, and every cause had a clear, calculable effect. It was a world of certainty, of solid objects and straightforward rules. If you knew the position and momentum of every particle, you could, in theory, predict the entire future of the universe. This comforting deterministic view reigned supreme for over 200 years. But at the dawn of the 20th century, as scientists began to probe the very smallest scales of existence, this elegant picture began to crack, revealing a world far stranger and more wondrous than anyone had ever imagined. Welcome to the realm of quantum physics. This is not just an extension of the old rules. It is a completely new operating system for the universe. It is the science of the infinitesimally small, the world of atoms and the particles within them, electrons, protons, and the quarks and photons that make up everything we see, touch, and are. Down here, in this subatomic domain, the familiar logic of our everyday world dissolves into a dizzying dance of probability and potential. The solid, predictable billiard balls of classical physics are replaced by ghostly waves of possibility. This is a world where particles don't have a definite location until we look at them. A world where a single electron can exist in multiple places at once. A state of being known as superposition. It's a place where particles can be mysteriously linked across vast cosmic distances, their fates intertwined in a phenomenon Einstein famously called spooky action at a distance, what we now call quantum entanglement. It's a reality where energy isn't continuous, but comes in discrete packets, or quanta, the very idea that gave this field its name. This radical departure from classical intuition didn't just add a new chapter to the book of physics. It forced us to tear up the book and start again. It fundamentally reshaped our understanding of reality itself, challenging our core assumptions about cause and effect, the nature of observation, and the very boundary between the observer and the observed. The pioneers of this revolution, Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, were reluctant heroes, often as baffled by their own discoveries as the rest of the world. They had unlocked a Pandora's box of cosmic secrets, and the implications were staggering. But this isn't just a historical curiosity or an abstract intellectual exercise. The bizarre rules of the quantum world are the bedrock of our modern technological society. The laser in your Blu-ray player, the transistors that power your smartphone, the medical imaging of an MRI scan, all are direct results of our understanding of quantum mechanics. And today, we stand on the precipice of a second quantum revolution. Scientists are harnessing these strange principles to build technologies straight out of science fiction. Ultra-powerful quantum computers capable of solving problems impossible for any classical machine, unbreakable cryptographic codes to secure our information, and even the tantalizing prospect of quantum teleportation. In this series, we will embark on a journey into this incredible world. We will explore the foundational experiments that shattered the classical worldview, meet the brilliant minds who pieced together this new reality, and demystify the core concepts of superposition, entanglement, and wave-particle duality. From the birth of the quantum idea to the cutting-edge technologies of tomorrow, prepare to have your perception of the universe turned upside down. This is the story of quantum physics, the story of reality itself. Let's explore the quantum basics: atoms, subatomic particles, and Planck's constant. At the heart of quantum mechanics lies a profound and baffling question. Is light a wave, or is it a particle? For centuries, we thought we knew the answer. In the early 1800s, Thomas Young's famous double-slit experiment seemed to settle it. He shone light through two narrow slits and observed an interference pattern on a screen behind them, alternating bright and dark bands. This pattern is a classic signature of waves. Think of ripples in a pond spreading out from 2 points. Where the crests of the waves meet, they amplify, creating a bright band. Where a crest meets a trough, they cancel out, creating a dark band. Case closed, right? Light is a wave. But the quantum world had a shocking surprise. We now know that light is also composed of discrete packets of energy called photons. So what happens if we turn the light source down so low that we fire only one photon at a time? Common sense dictates that each photon, like a tiny bullet, must pass through either the left slit or the right slit. Over time, we should see just 2 bright bands on the screen, directly behind the slits. But that's not what happens. Incredibly, even when sent one by one, the photons gradually build up the exact same interference pattern as before. It's as if each individual photon somehow passes through both slits at once, interferes with itself, and then lands on the screen as a single localized particle. This is the essence of wave-particle duality. The photon travels as a wave of probability, exploring all possible paths simultaneously. The mystery deepens even further. If we place a detector at the slits to see which path the photon takes, the interference pattern vanishes completely. The very act of observation forces the photon to choose a path and behave like a simple particle. This duality isn't just for light. Electrons, atoms, and even large molecules have been shown to exhibit this strange behavior. It's a fundamental principle of reality, challenging our everyday intuition and forming the bedrock of the quantum revolution. Quantum superposition, Schrödinger's cat, objects existing in multiple states at once. Quantum entanglement, Einstein's spooky action at a distance. From the mind-bending theories we've explored, quantum mechanics has blossomed into a technological revolution that is actively shaping our present and defining our future. It's not just abstract mathematics and philosophical debate, it's the engine behind some of the most powerful tools humanity has ever conceived. Perhaps the most exciting frontier is quantum computing. Classical computers, like the one you're likely watching this on, think in bits, ones and zeros. It's a binary black and white world. But quantum computers operate on a completely different level. They use qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. And thanks to entanglement, the states of multiple qubits can be linked in a complex dance, no matter how far apart they are. By harnessing these properties, a quantum computer can explore a vast number of possibilities simultaneously. While a classical computer tries every key to a lock one by one, a quantum computer can essentially try them all at once. This incredible power won't replace your laptop, but it promises to solve problems currently impossible for any supercomputer, designing life-saving drugs by simulating molecules with perfect accuracy, creating novel materials with unimaginable properties, and optimizing complex global systems. We are at the dawn of this new computing age, and the possibilities are staggering. But with great power comes great risk. The very same power that allows a quantum computer to design new medicines could also be used to shatter the digital security that underpins our modern world. Most of our current encryption methods rely on mathematical problems that are too difficult for classical computers to solve. For a mature quantum computer, however, breaking this encryption would be trivial. This creates a quantum threat to our banking, communications, and national security. But quantum physics provides not only the poison, but also the antidote, quantum cryptography. The most promising method is quantum key distribution, or QKD. It works on a simple quantum rule. You can't measure something without disturbing it. The key is encoded onto individual photons. If a spy intercepts them, the act of measuring alters the photons, creating detectable errors. This immediately alerts the users to the breach. It's security guaranteed by the laws of physics. While quantum computing feels futuristic, you are already living in a world built by quantum mechanics. Every time you use your smartphone or computer, you are using technology that would be impossible without it. The heart of all modern electronics is the semiconductor, and its behavior is purely quantum. Inside a silicon chip are billions of tiny switches called transistors. Our ability to control the flow of electrons through these transistors depends on understanding quantum concepts like energy bands and quantum tunneling. It was by mastering the quantum behavior of electrons and materials that we learned to create these microscopic switches, paving the way for the entire digital age. And what about the laser? From barcode scanners to the fiber optic cables that carry the internet, lasers are everywhere. The word laser is an acronym for light amplification by stimulated emission of radiation. That stimulated emission is a quantum process. In simple terms, atoms are pumped to a high energy state. One atom releases a photon, which stimulates other excited atoms to release a cascade of identical photons. This creates the perfectly coherent, focused beam of light we know as a laser. Beyond these incredible technologies, the quantum revolution has forced us to confront the deepest questions about the nature of reality itself. For centuries, classical physics gave us a comforting vision of a clockwork universe, a deterministic cosmos where, if you knew the position and momentum of every particle, you could predict the future with absolute certainty. Quantum mechanics shattered this deterministic dream. At the fundamental level, the universe isn't a clock, it's a casino. The wave function doesn't tell us what a particle is doing, but rather the probabilities of what it might be found doing upon measurement. This inherent randomness deeply troubled physicists like Einstein, who famously declared, "God does not play dice with the universe." Yet experiment after experiment has confirmed this probabilistic nature is a core feature of our reality. This leads to an even stranger question. What is reality when we're not looking at it? Does a particle even have a definite position before we measure it? The Copenhagen interpretation suggests properties like position are undefined until measurement forces an outcome. In a sense, the observer helps create the reality they observe. Other interpretations offer even more radical alternatives. The many worlds interpretation proposes that the universe never chooses at all. Instead, every possible outcome of a quantum measurement occurs, each in its own separate parallel universe. Every time a quantum event happens, the universe branches. In one universe, the particle was found here. In another, it was found there. In this view, there is a near infinite tapestry of parallel realities, and we are simply experiencing one path through it. From the transistors in our pockets to the philosophical debates about parallel worlds, quantum physics has completely rewritten our understanding of the universe. It took us from a predictable clockwork cosmos to a strange, probabilistic reality woven from uncertainty and potentiality, and the journey is far from over. The greatest challenge in physics today is to unite quantum mechanics with general relativity to create a theory of everything. What will such a theory reveal? Will it explain the mysteries of dark matter and dark energy? Will it tell us what happens in a black hole, or what the universe was like at the Big Bang? Could it even shed light on the nature of consciousness itself? 100 years ago, we had no idea the quantum world even existed. Now, we are harnessing its power and grappling with its profound implications. If the first quantum revolution rewrote the rules of reality, we can only wonder what the next one will reveal. The universe is stranger and more mysterious than we ever imagined, and the quest to understand it is the greatest adventure of all. The quantum realm is the ultimate frontier, a place of deep mystery and infinite possibility. If you're as fascinated by these questions as we are, and you want to continue exploring the cutting edge of science and the fundamental nature of reality, then join our community of curious minds. Subscribe to PhysicsAI for more deep explorations into the cosmos and our quantum world. Thank you for watching.
What if I told you that even black holes, the most powerful objects in the universe, are slowly dying? It sounds impossible. These cosmic titans, with gravity so immense that not even light can escape, are the universe's ultimate symbols of permanence. But in the strange world of theoretical physics, even the eternal has an end. To understand this cosmic paradox, we first need to grasp what a black hole truly is. They are born from the death of colossal stars. When a star at least 20 times more massive than our sun exhausts its nuclear fuel, it collapses under its own immense gravity. This cataclysmic implosion crushes its core into an infinitely dense point called a singularity, creating a region of space-time where gravity is so strong that nothing can escape. This boundary is the event horizon, the point of no return. For a long time, we believed anything crossing it was lost forever, making black holes seem like eternal cosmic prisons. But in 1974, the legendary physicist Stephen Hawking changed everything. By merging Einstein's theory of gravity with the bizarre rules of quantum mechanics, he made a startling discovery. Black holes are not completely black. They must emit a faint thermal glow, now known as Hawking radiation. The secret lies in the quantum vacuum of empty space, which isn't empty at all. It's a fizzing soup of virtual particle pairs that pop into existence and annihilate each other almost instantly. Hawking theorized that if a pair forms right at the event horizon, one particle can fall in while its partner escapes. To an outside observer, it appears as if the black hole itself has just radiated a particle away. Empty space isn't truly empty. It's a seething foam of virtual particles that constantly pop into existence as particle-antiparticle pairs before annihilating each other. But at a black hole's event horizon, if a pair appears, one can fall in while the other escapes. The infalling particle has negative energy, subtracting from the black hole's mass. The escaping particle becomes real, carrying away energy as radiation. This is Hawking radiation, a process ensuring every black hole will eventually evaporate completely. The rate of this evaporation depends on size. A smaller, stellar mass black hole is hotter and radiates away its mass much faster than a colossal supermassive one. A solar mass black hole would take 10 to the 67th power years to disappear. Supermassive black holes, however, will last for an almost eternal 10 to the 100th power years, outliving everything else. This leads to the distant black hole era. After the last stars fade, the universe will be a dark, cold cosmos populated only by these slowly dying giants, silently radiating their mass into the void. As a black hole shrinks, its evaporation accelerates, culminating in a final brilliant flash of gamma rays. It erases itself from existence, leaving behind an almost empty universe filled with a faint whisper of radiation. Black holes may be the kings of the cosmos today, but even kings don't rule forever. Through the slow process of Hawking radiation, they will eventually evaporate over unimaginable timescales. Their story is a profound reminder of cosmic evolution. If you're fascinated by these mysteries, subscribe and join our journey. Explore more mind-bending topics with us right here.
What if the sun suddenly vanished during the day or the moon disappeared at night? Well, these aren't science fiction scenarios. They're real phenomena that happen right here in our solar system. Welcome to PhysicsAI, where we explore the incredible physics of our universe. Today, we're diving into one of nature's most spectacular shows, eclipses. And trust me, the physics behind them is absolutely mind-blowing. Let's start simple. Imagine you have a lamp and a ball. When light from the lamp hits the ball, it creates a shadow. That shadow is simply an area where light has been blocked. Now scale this up to cosmic proportions. We have our sun as the light source, and both Earth and Moon can act as the ball, casting shadows into space. These shadows have two parts, the umbra, which is the dark inner shadow, and the penumbra, the lighter outer shadow. An eclipse happens when the sun, Earth and Moon line up in what astronomers call syzygy. But depending on the order of this alignment, we get two completely different types of eclipses. A solar eclipse occurs when the moon passes between the sun and Earth, casting its shadow on our planet. The moon's shadow races across Earth's surface at over 1,500 miles per hour, creating a path of totality. In a total solar eclipse, the moon completely covers the sun's bright disk, revealing the sun's beautiful corona, its outer atmosphere. In a partial eclipse, the moon only covers part of the sun, creating that famous crescent shape. And in an annular eclipse, the moon appears smaller than the sun, creating a spectacular ring of fire effect. This happens because the moon's orbit is elliptical, so sometimes it appears larger or smaller in our sky. Here's the incredible coincidence. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away. This means they appear almost exactly the same size in our sky, making total solar eclipses possible. Remember, never look directly at the Sun during an eclipse without proper eclipse glasses. It can cause permanent eye damage. A lunar eclipse is the opposite scenario. Earth passes between the Sun and Moon, casting Earth's shadow on the lunar surface. Earth casts a much larger shadow than the Moon, which is why lunar eclipses last much longer, sometimes over an hour. During a total lunar eclipse, the Moon doesn't disappear completely. Instead, it turns a beautiful deep red colour. This happens because Earth's atmosphere acts like a lens, bending red light around our planet and onto the Moon's surface. Blue light gets scattered away by our atmosphere, but red light makes it through, giving the Moon that eerie blood-red appearance. In a partial lunar eclipse, only part of the Moon enters Earth's shadow, and in a penumbral eclipse, the Moon only passes through Earth's outer shadow, causing just a subtle dimming. Unlike solar eclipses, lunar eclipses are visible from anywhere on Earth's night side simultaneously. Now you might wonder, if the Moon orbits Earth every month, why don't we get eclipses every month? The answer lies in orbital mechanics. The Moon's orbit is tilted about 5 degrees relative to Earth's orbit around the Sun. This means most of the time the Moon passes slightly above or below the Sun-Earth line, missing perfect alignment. Eclipses can only happen when the Moon crosses Earth's orbital plane at points called nodes. These alignments create eclipse seasons that occur roughly every 6 months, when we can have multiple eclipses in a short period. On average, any given location on Earth sees a total solar eclipse only once every 375 years, making them incredibly rare and special events. Eclipses are not just cosmic coincidences, they are windows into the precise and beautiful clockwork of our universe. They remind us that we live in a dynamic solar system where celestial mechanics create these incredible natural phenomena. If you love cosmic physics explained simply, subscribe to PhysicsAI for more mind-bending science videos. Until next time, keep looking up and questioning the incredible physics all around us.
What if the loudest sound in the universe wasn't just deafening, but deadly? What if the end of the world wasn't a flash of light or a fiery explosion? What if it was a sound? Not a scream or a bang that you could hear with your ears, but something far more fundamental. A vibration so immense, so overwhelmingly powerful, that it could unravel the very fabric of our planet. Imagine, just for a moment, a wave of pure energy, born from a single catastrophic event, rippling through the ground, rippling through the sea, rippling through the air. To understand how sound could destroy a world, we first have to understand what it is. Sound is simpler than you might think. It's a journey of energy. When you clap your hands, you disturb the air molecules around them, pushing them together. These compressed molecules then push on their neighbors, who push on their neighbors, and so on. This creates a chain reaction, a traveling wave of high and low pressure that ripples through the air. We measure the intensity of this energy using a scale called decibels. A quiet whisper is around 30 decibels. A rock concert might hit 120 decibels, which is the threshold of pain for our ears. Every increase of 10 decibels represents a 10-fold increase in sound energy. The scale is logarithmic, meaning it grows incredibly fast. This energy is real, it's physical. A loud enough sound can do more than just hurt your ears, it can exert a physical force. At around 190 decibels, the pressure waves are so intense they can rupture your eardrums and even cause shock waves in the air itself. This is the level of a rocket launch heard from up close. Let's imagine cranking up the volume. Not just to the level of a rock concert, but far, far beyond. At around 200 decibels, the pressure waves would be powerful enough to shatter glass windows and cause structural damage to buildings. Cities would begin to tremble, not from an earthquake, but from the sheer force of the air pressing against them. As we climb higher, the effects become apocalyptic. At 250 decibels, the sound pressure would be so immense it could move the oceans themselves, creating massive tsunamis that would scour the continents clean. The sound would be a physical hammer, striking the planet with relentless force. To actually crack the Earth's crust, we would need a sound of truly astronomical intensity. We're talking about a sound wave with a magnitude somewhere around 300 decibels. A continuous sound at this level would inject so much vibrational energy into the ground that it would liquefy solid rock. The ground would behave like water, creating waves of stone hundreds of feet high. Tectonic plates would grind against each other uncontrollably, triggering earthquakes of a magnitude never before witnessed. The Earth would literally be shaken to pieces from the inside out. But why stop there? Let's consider the energy needed to destroy the planet entirely. The Earth would cease to exist, vaporized into a rapidly expanding cloud of superheated gas and rock, its final scream echoing into the void. As powerful as our imaginary Earth-destroying sound is, the universe honestly plays on an entirely different scale. The loudest sounds in the universe are generated by the most violent events imaginable. Consider a supernova, the explosive death of a massive star. When a star explodes, it releases more energy than our sun will produce in its entire lifetime. This explosion sends a shockwave, a sound wave of unimaginable power, racing through the interstellar gas. But even a supernova, honestly, pales in comparison to the collision of two black holes. When these cosmic titans, each with the mass of millions of suns, spiral in towards each other, they violently warp the fabric of spacetime itself. In the final moments before they merge, they are moving at nearly the speed of light, releasing an incredible burst of energy in the form of gravitational waves. The power released in this single event is more than the light from all the stars in the observable universe combined. If we could somehow translate the energy of that black hole merger into a sound wave in our atmosphere, the decibel level would defy comprehension. And what about the loudest sound of all time? That likely occurred at the very beginning of the universe. During the inflationary period, just a fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This hyperexpansion would have created colossal sound waves, rippling through the hot, dense plasma of the early cosmos. These primordial sound waves, known as baryon-acoustic oscillations, were so vast that they stretched for hundreds of thousands of light years. They were the vibrations that helped seed the large-scale structures of the universe, shaping the cosmic web of galaxies we see today. The universe was born in a roar, not a whisper. We have journeyed from a simple clap of the hands to the collision of black holes. We've seen how sound, a mere vibration, can be scaled up to a force of planetary and even galactic annihilation. It forces us to confront the sheer power inherent in the physical laws of our universe. The same energy that carries a melody can, in sufficient quantity, unmake the very matter that melody is played upon. This exploration leads us to a final profound question. We have imagined a sound powerful enough to destroy a planet and even a solar system. But what are the ultimate limits? Is there a theoretical maximum volume in the universe? A point where the energy density of a sound wave becomes so great that it collapses in on itself, forming a black hole made of pure sound. Could a sound wave carry enough energy to tear a hole in the fabric of space-time itself? The laws of physics as we currently understand them suggest there are limits. But what if, in the far future, or in another corner of the multiverse, the rules are different? Could there exist a sound so powerful, a vibration so fundamental, that it could continue to grow in intensity without limit? A wave that could propagate from one universe to the next, a crescendo that never ends. If a sound wave could be amplified indefinitely, could it unravel everything? Could a single ultimate vibration, a final infinite chord, erase all of existence? Could it undo the Big Bang itself, returning the entire cosmos to the silent, featureless singularity from which it came? We may never know the answer, but asking the question expands our imagination and deepens our appreciation for the fragile, beautiful, and sometimes violent symphony of the cosmos. It reminds us that in the grand orchestra of existence, we are both the audience and a fleeting part of the music.
Imagine looking up at the night sky. But tonight, something is profoundly wrong. The familiar, comforting glow of the moon is gone, vanished. Only an unnerving, star-dusted emptiness remains. The darkness feels deeper, more absolute. This is not just a loss of light. It is the beginning of a great unraveling. What if the moon simply disappeared tomorrow? The consequences would be immediate and catastrophic. Our planet suddenly alone set adrift, balance shattered. The first change, the loss of its gentle, silvery light. Nights become impenetrably dark, like the deepest caves. Nocturnal animals timed to the lunar cycle would be plunged into confusion. Predators that hunt by moonlight would starve. Prey that forage by dim light would be forced to rely on sound or smell. The rhythms of life, honed over millions of years, would be broken. Our planet does not sit perfectly upright as it journeys around the sun. It leans. This axial tilt, a gentle inclination of about 23.5 degrees, is the very reason we have seasons: spring, summer, autumn, winter. But this stability is not an accident. It is a gift from the moon. Our large satellite acts like a gravitational gyroscope, a planetary pacifier, holding Earth's tilt steady and preventing it from wobbling chaotically through space. Without the moon's steadying influence, Earth's axial tilt would become dangerously erratic. Over thousands of years, it could swing wildly, perhaps tilting to nearly 90 degrees, like the planet Uranus, or straightening up completely. The seasons as we know them would cease to exist. Instead, we would face periods of unimaginable climate extremes. Imagine a world where the North Pole points directly at the sun for decades. Twice each day, the oceans of our world breathe. They rise and fall in a steady, powerful rhythm. This is the pulse of the planet, the tides, driven primarily by the immense gravitational pull of the moon. As the moon orbits our planet, its gravity tugs on the water, creating a bulge on the side of Earth facing it and another on the opposite side. If the moon were to vanish, this ancient, powerful pulse would not stop entirely, but it would be drastically weakened. The great ocean tides would shrink to less than a third of their current size, becoming mere whispers of their former glory. This dramatic reduction would have immediate and devastating consequences for the intertidal zone. This is the sliver of our world that is both land and sea, a place of incredible biodiversity. Mussels, barnacles, sea stars, crabs. With the tides greatly diminished, vast swaths of these rich ecosystems would be left high and dry, permanently exposed to the air. Weaker tides would mean less mixing, leading to stagnant oxygen-poor zones in the ocean. For billions of years, life on Earth was confined to the oceans. It was a world of aquatic creatures, a planet whose land was utterly barren. The great leap from water to land was one of the most pivotal moments. But this momentous step may never have happened without the moon. The vast rhythmic tides driven by the moon's pull formed the intertidal zone. Tidal pools were alternately flooded with seawater, then exposed to harsh sun and air. They acted as a crucial evolutionary training ground. Think of these pools as nature's laboratory. Aquatic organisms were repeatedly faced with terrestrial challenges. They had to prevent themselves from drying out. They had to breathe air when the water receded. They had to support their own bodies without water's buoyancy. Creatures with primitive lungs, skin that retained moisture, or fins that propped them up on mud gained an advantage. This zone was the bridge between sea and land. The moon's gravity was the architect of that bridge. Without a large moon to create big tides, the transition zone would have been far less dynamic. When we look at the moon, we do not just see a rock in the sky. We see the ancient force that may have coaxed our most distant ancestors from the sea and set them on the path that would lead to humanity. When the Earth first formed, it spun much, much faster than it does today. A day may have lasted only 6 hours. Over billions of years, the gravitational pull of the moon has acted as a brake, gradually slowing our planet's rotation down to the familiar 24-hour cycle we now experience. If the moon were to disappear, this braking force would be gone. The primary force slowing our planet would vanish. Conservation of angular momentum would take over, and the Earth's rotation would begin to gradually speed up. Days would become shorter. A day might shrink from 24 hours to 20, then 15, then perhaps back to the frantic 6 to 8 hour days of Earth's infancy. A faster spin would completely reshape our planet's weather. The Coriolis effect, the force that creates the rotational patterns of storms like hurricanes, is directly linked to the speed of the planet's rotation. A faster spin would mean a much stronger Coriolis effect. Weather systems would become far more extreme. Winds would howl at incredible speeds, potentially hundreds of miles per hour. Life, which has evolved in rhythm with a 24-hour day, would struggle to adapt. The circadian rhythms of plants, animals, and even humans are deeply ingrained. As we gaze up at the moon, it is easy to see it as a beautiful but passive object, a mere decoration in our night sky, a source of myth and wonder. But its true role is far more fundamental. It is not an ornament. It is a cornerstone of our world's architecture. It is the silent guardian that has held our planet steady, the cosmic partner that has stirred our oceans, the patient guide that may have led life itself onto land. The world without a moon would be an alien planet. It would be a place of violent extremes, of shrieking winds and chaotic climates, a world where the seasons are a lottery of fire and ice. Its oceans would be sluggish and its lands perhaps forever barren. The story of Earth is inextricably linked to the story of its moon. They are not two separate bodies, but a single, dynamic system, a partnership forged in a cataclysmic collision billions of years ago. Every ecosystem, every species, every aspect of our planet's climate is, in some small way, a testament to this ancient partnership. So the next time you look up at that familiar luminous orb, remember what you are truly seeing. You are not just looking at a satellite, a piece of rock caught in our gravity. You are looking at the reason our world is not a wobbling, storm-racked wasteland. You are seeing the distant force that stirs our oceans, steadies our seasons, and may have made our very existence possible. The moon is not just a light in the darkness. For all of us on this fragile blue planet, it is a vital part of what makes Earth home. The moon doesn't just light our night skies. It may be the reason we're here at all.
Have you ever gazed up at the night sky on a clear, dark evening, and have you noticed how the stars seem to sparkle and dance, putting on a celestial show just for you, while other bright points of light shine with a steady, unwavering glow? That steady light is very likely a planet, a celestial neighbor in our solar system. Perhaps it's Venus, our brilliant morning star or evening star. Or maybe it's Jupiter, the giant of our solar system, shining brightly. So what accounts for this difference? Why do stars twinkle with such enchanting irregularity, but planets don't seem to join in the dance? The answer to this cosmic riddle isn't hidden out in the vast expanse of space, among the stars themselves. It's actually much closer to home, residing right here on Earth, surrounding us every day. The twinkling, or scintillation of stars is primarily caused by the dynamic nature of our planet's atmosphere. As starlight, after traveling immense distances, finally travels through the turbulent and ever-changing air above us, it bends and shifts in unpredictable ways, a phenomenon known as refraction. This constant bending and unbending of light rays is what makes stars appear to shimmer and twinkle. Planets, on the other hand, present a different picture. They generally shine with a calm, steady glow, resisting the twinkling effect. The star itself isn't actually flickering or changing its light output. It's a stable source of illumination. It's solely the journey its light undertakes through our dynamic and somewhat chaotic atmosphere that creates the twinkling effect we observe. In essence, our atmosphere acts like a giant, imperfect, and constantly shifting invisible lens, subtly and continuously distorting the light emanating from those incredibly distant stars. As that starlight embarks on its journey, traversing trillions of miles of empty space, it maintains a remarkably straight and unwavering path, undisturbed by any atmospheric effects, until the very last instant of its long voyage, just before it reaches our world, when it finally encounters Earth's protective atmospheric layers. And that's when the real fun, or rather, the real distortion, begins. The constantly swirling and mixing layers of air, with their varying temperatures and densities, bend and scatter the incoming light, effectively transforming what was once a steady and direct beam of light into the captivating twinkle we observe from the ground. So, the beloved children's song, "Twinkle, Twinkle, Little Star," is, in a way, a bit misleading from a scientific perspective. The star itself isn't truly twinkling. It's the star's light that's undergoing the twinkling transformation. By delving into this seemingly simple question of why stars twinkle, we gain valuable insights not just about the nature of stars themselves, but also about the characteristics of our own planet, its atmosphere, and our place within the vast and awe-inspiring universe beyond. So, let's dive deeper into the fascinating science behind why stars appear to twinkle in the night sky, and explore the reasons why planets, for the most part, maintain a steadier and more constant glow. Prepare yourself to see the night sky and everything in it in a whole new and illuminating way. The scientific name for twinkling is atmospheric scintillation. It simply means the sparkling effect caused by our atmosphere. Imagine looking at a coin at the bottom of a still pool. It looks clear and steady, but if the water ripples, the coin seems to wiggle and shimmer. That's what happens to starlight as it passes through our turbulent air. This bending of light is called refraction. You've seen it before, like a straw looking bent in a glass of water. Our atmosphere is made of many layers, each with different temperatures and densities. As starlight enters from space, it passes through these shifting layers, bending again and again. Because the air is always moving, the path of the light is constantly changing. This makes the star's image dance and flicker, creating the twinkling effect we call scintillation. It's a dazzling light show, courtesy of our ever-changing sky. That's the science behind the sparkle. Have you ever gazed up at the night sky and wondered, why do stars seem to twinkle with such vibrant energy, while planets, in contrast, appear to shine with a steady, unwavering light? It's a question that has intrigued stargazers for centuries. The answer, surprisingly, comes down to a simple matter of how these celestial bodies appear to us from our vantage point here on Earth. It's all about their apparent size and how their light interacts with our atmosphere. Stars are incredibly far away, so distant in fact that to our eyes, even with the aid of powerful telescopes, they look like single, infinitesimally small points of light. Astronomers refer to these distant objects as point sources because their light originates from what appears to be a single, concentrated location. As a result of this extreme distance, their light reaches us as a thin, incredibly narrow beam, almost like a laser pointer shining across vast distances. This delicate beam is easily disturbed and distorted as it passes through the Earth's turbulent atmosphere, encountering pockets of air with varying temperatures and densities. Planets, while still incredibly distant in their own right, are significantly closer to us than the stars. They reside within our own solar system, relatively nearby on a cosmic scale. Because of their relative proximity, they don't appear as mere points of light. Instead, they appear as tiny, albeit still very small, disks in the sky. This is true even if we can't readily discern that shape with our naked eyes. Telescopes reveal their disk-like nature, even if subtle. To understand the difference, imagine a single, solitary laser beam versus a cluster or bundle of many such beams, all traveling together. If the single beam encounters any disturbance, it will wobble and dance erratically, its path easily deflected. However, the cluster of beams will remain much steadier because the individual disturbances affecting each beam tend to average out across the entire group. And that's precisely what happens with the light from planets as it journeys through our atmosphere. Because their light originates from a small disk rather than a single point, the atmospheric disturbances affecting different parts of the disk tend to cancel each other out, creating a more stable and consistent light source. The end result? Stars twinkle dramatically, their light scattered and distorted, while planets shine with a steady, unwavering glow. This seemingly simple difference in apparent size between a point and a disk is the key that unlocks this celestial mystery. So the next time you gaze up at the night sky and notice a steady, unwavering light shining among a sea of twinkling stars, you're likely looking at a planet, a nearby neighbor in our cosmic backyard. Ultimately, it's all about distance and perspective, how far away these objects are and how they appear to us from our unique vantage point. The universe is a vast and wondrous place full of countless surprises and hidden secrets waiting to be discovered. And sometimes, as we've seen, the smallest details, a subtle difference in apparent size, can make the biggest difference in how we perceive and understand the cosmos. That's the beautiful secret behind the planet's calm, serene glow, a testament to the power of perspective and the wonders of the universe. The journey of starlight as it pierces through our atmosphere is a fascinating one. It's a voyage from the distant cosmos to our very eyes. But this journey is anything but smooth and uneventful. It's a bumpy ride, full of twists and turns. The air above us isn't a uniform blanket. Instead, it's a chaotic mix of constantly moving pockets, swirling and shifting. Each of these pockets possesses different temperatures and densities, creating a constantly fluctuating environment. As a thin ray of starlight, a delicate messenger from afar, enters this turbulent atmospheric layer, it doesn't travel in a straight line. Instead, it bends and zigzags erratically, undergoing these deflections thousands of times each second, a truly rapid and chaotic dance. From our perspective on the ground, this constant bending causes the star to seem to jiggle and flicker, its brightness fluctuating in a mesmerizing way. Sometimes these air pockets, with their varying densities, act like tiny, imperfect lenses, briefly focusing the starlight, making it appear brighter or dimming it, causing it to fade momentarily. This rapid brightening and dimming, this constant oscillation in the star's light, is precisely what we perceive as the enchanting twinkle of a star. Occasionally, under just the right conditions, the atmosphere can even split the star's light, separating it into its constituent colors, creating fleeting flashes reminiscent of a mini prism. Most of the time, these subtle color changes happen far too quickly for our eyes to consciously register, but they contribute to the overall shimmering and ethereal quality of the starlight we observe. So the next time you gaze up and see a star twinkle in the night sky, remember that you're witnessing a complex and beautiful dance, an intricate interaction between light and the air above us. It's a beautiful and humbling reminder, a testament to the wonders of nature, of the powerful yet often invisible atmospheric forces constantly at play in the world above us. The night sky, far from being a static canvas, is actually a dynamic and ever-changing spectacle. Have you noticed stars twinkle more near the horizon? That's no illusion. When a star is low in the sky, its light travels through a thicker slice of atmosphere. The longer slanted path means more turbulence, more bending, and more twinkling. Stars overhead pass through less air, so they appear steadier. That's why astronomers prefer to observe objects high in the sky, where the view is sharpest. If you want to see the most dramatic twinkling, look near the horizon. It's a vivid reminder of the deep ocean of air above us. The next time you're stargazing, notice how the twinkle changes with height. The sky's show is always changing, depending on where you look. Even the position of a star can change how it sparkles. So why don't planets twinkle? It's all about how their light reaches us. Planets appear as tiny disks, sending many light rays through the atmosphere at once. Each ray gets bent and jostled, but the effects average out. Our eyes blend all these tiny fluctuations into one steady image. That's why planets shine with a calm, unwavering glow. The atmosphere affects their light just as much as it does starlight, but we can't see the twinkle. It's a perfect example of how size and distance change our view of the universe. So, when you spot a steady light among the twinkling stars, you're seeing a planet. Now you know the secret behind their serene shine. The universe is full of wonders, and sometimes the explanation is right above our heads. Keep looking up. You never know what you'll discover. Twinkling stars are beautiful, but for astronomers, they're a challenge. The atmosphere blurs and distorts images, making it hard to study distant objects. For years, observatories were built on mountaintops to minimize this effect. Today, technology called adaptive optics helps untwinkle the stars. Flexible mirrors and telescopes adjust in real time to correct for atmospheric distortion. This lets astronomers capture sharp, clear images from the ground. Thanks to adaptive optics, we can now see the universe in stunning detail, right from Earth. The next time you see a twinkling star, remember, science is always finding new ways to see the cosmos more clearly.
Look around you. Everything seems solid and real. Tables, chairs, the screen in front of you. We trust the world is stable, that things exist whether or not we're looking. But what if this sense of reality is just an illusion? Physics, especially quantum physics, challenges our most basic assumptions. As we probe deeper, the universe appears less like a machine and more like a shifting landscape, shaped by our observations. Imagine a world that only becomes detailed when you interact with it, like a video game rendering new terrain as you explore. Could reality itself depend on our participation? This journey will reveal a universe far stranger and more mysterious than we ever imagined. For centuries, classical physics painted the universe as a predictable clockwork machine. Everything had a definite position and momentum, whether or not anyone was watching. Reality was objective and independent, like a billiard ball rolling across a table, its path certain even with your eyes closed. This worldview let us build bridges, launch rockets, and trust in the stability of nature. The laws of physics seemed absolute, describing a universe that existed with or without us. But as we looked closer, cracks appeared. At the atomic scale, the rules changed. The certainty of classical physics gave way to the strangeness of quantum mechanics. Suddenly, reality wasn't as solid as we thought. The universe was about to get very, very strange. The double-slit experiment. A cornerstone of quantum mechanics, it's an experiment that continues to baffle and inspire physicists to this day. It elegantly demonstrates the wave-particle duality of matter. Challenging our most basic assumptions about reality, it shattered our classical expectations, forcing us to reconsider the very nature of reality at the smallest scales. The implications of this experiment are profound, touching upon the foundations of physics and our understanding of the universe. Fire electrons one by one towards a barrier. These tiny particles, the fundamental building blocks of matter, are about to reveal a surprising secret, one at a time through two slits, meticulously crafted in a barrier. Classically, we'd expect each electron to pass through one slit or the other, and you'd expect two bands on the screen, corresponding to the electrons that pass through each slit. A simple, predictable outcome, or so it seems, like tiny billiard balls, each following a definite trajectory. This is what our intuition, based on the macroscopic world, would lead us to believe. But instead, you see an interference pattern, a series of alternating bands of high and low intensity. This is a hallmark of wave behavior, a pattern created by the superposition of waves, as if each electron is a wave, spreading out and interfering with itself. How can a single particle behave like a wave? This is the central mystery of the double-slit experiment, passing through both slits at once. It's as if the electron explores all possible paths simultaneously, a concept that defies classical logic. Each electron seems to exist in a superposition, a combination of multiple states at the same time. It's a blurry, probabilistic existence, unlike the definite reality we experience every day, taking all possible paths until measured. The electron exists in a state of uncertainty, a cloud of potential, until an observation is made. The act of measurement changes everything. It forces the electron to choose a single state, collapsing the superposition. If you check which slit the electron goes through by placing a detector at one of the slits, something remarkable happens. The interference vanishes. The wave-like behavior disappears as if by magic. The electron acts like a particle again, passing through only one slit and creating the expected two bands on the screen. It's as if the electron knows it's being watched and changes its behavior accordingly. This raises profound questions about the role of the observer in shaping reality. The very act of observation, the act of gaining information, fundamentally alters the system being observed, forces it to choose a single reality, a single path, from the multitude of possibilities. This experiment reveals a universe at its most fundamental level, where particles are clouds of probability, existing in a state of potential, not solid objects, with definite properties and fixed locations. Reality at its core is far more fluid and uncertain than our everyday experience suggests, is not fixed until we look, until we make a measurement and collapse the wave function. The double-slit experiment is a window, a glimpse, into the quantum world's deepest mysteries, challenging our understanding of reality itself. Our role as observers, as conscious beings interacting with the universe, is far more active than we ever imagined, shaping the very fabric of reality through the act of observation. The double-slit experiment, a cornerstone of quantum mechanics, leads to the observer effect, a mind-bending concept where the very act of observation observing changes reality. It suggests that the universe isn't a fixed, predetermined entity, but rather, before measurement, an electron exists as a wave of possibilities, a range of potential states, a superposition. It's in multiple places at once, in a probabilistic cloud. Measurement collapses this wave, forcing the electron to choose a single location, into a single outcome, a definite, measurable state. This isn't about human consciousness. It's not about the power of the mind. Any interaction that records information counts. Any process that encodes the state of the electron, the universe chooses a reality, selecting one possibility from many. The moment information is captured, the moment the wave function collapses. Quantum properties like position, things we take for granted in our everyday lives, or momentum, the measure of how much force is required to stop something, may not exist until measured. They are created by the act of measurement itself. At the quantum level, reality is participatory. We are active participants in shaping what we perceive, a dynamic process shaped by measurement. It's a dance between possibility and actuality. Our everyday experience hides this strangeness because we are dealing with vast numbers of particles. But at the smallest scales, where quantum effects dominate, reality is fluid and uncertain. It's a realm of probabilities, not certainties. The act of observation sculpts the world, like a sculptor shaping clay, from a haze of possibilities, from a quantum fog of potential realities. This raises a profound question, a question that has puzzled physicists for decades. If reality depends on measurement, what was happening before observers existed, before life emerged? Was the universe indefinite, a vast, unformed potential until something measured it, until the first interaction that recorded information? The quantum world challenges our deepest intuitions. It forces us to rethink our understanding of reality. We are not just spectators, passive observers of a pre-existing universe. We help create reality itself. We are active participants in the unfolding cosmic drama. To make sense of quantum strangeness, physicists developed the Copenhagen interpretation. It says, stop asking what particles really do when unobserved. Physics describes what we can measure, not what is. The quantum world is governed by probabilities, not certainties. Measurement bridges the quantum and classical worlds, collapsing possibilities into outcomes. The universe is fundamentally random. Chance is built into its fabric. The Copenhagen view works, but it leaves many unsatisfied. It avoids the question of why measurement matters, treating the observer as special. For some, this feels like dodging the real mysteries of existence. Dissatisfaction with Copenhagen led to wild new ideas. The many worlds interpretation says every possible outcome happens in parallel universes. When you measure an electron, reality splits in one world, it goes left in another, right. Every quantum event creates new branches of reality. Another view, cubism, puts the observer at the center. Here, the wave function reflects your personal knowledge, not objective reality. Measurement updates your beliefs, not the world itself. Each observer has their own version of reality shaped by experience. Quantum mechanics becomes a tool for navigating uncertainty, not a description of what is. These interpretations make reality more participatory and subjective than we ever imagined. The universe may be a conversation between us and the world, not a fixed stage. Maybe the problem isn't just a missing piece of the puzzle or a gap in our understanding. Perhaps our logic itself, the very foundation upon which we build our understanding, may not fit the quantum world. We've been trying to force a square peg into a round hole, using tools designed for a different reality. Classical logic, the bedrock of our reasoning, dictates that things are either true or false, a simple binary choice. Something is either here or not here, existing or not existing, a definitive state. But quantum logic throws a wrench into this neat dichotomy, allowing for superpositions. These are states that are both and neither, existing in a probabilistic limbo until observed. It's a concept that challenges our fundamental intuitions. The famous double-slit experiment dramatically shows that particles can exist in multiple states simultaneously, a wave of possibilities, until the moment of measurement forces them to choose a single reality. Imagine a video game where a character is both safe and in danger, alive and dead, at the same time. This is until you interact with the game, until you make a choice. What if the universe's underlying code, the very fabric of reality, is written not in the language of classical rules, but in the strange and wonderful language of quantum logic, not in the deterministic clockwork of classical rules? This paradigm shift leads us to the ultimate question. If observation collapses the quantum state, who or what was the first observer? Did the universe exist in a haze of infinite possibilities, a sea of potential realities? Until something, somewhere, measured it, forcing it to coalesce into the reality we perceive? Standing at the edge of knowledge, we confront the profound mystery of existence, a mystery that deepens with every new discovery. And we begin to question our role, our influence, in shaping the very fabric of reality. The quantum world invites us to rethink everything, to challenge the assumptions we thought we knew, and to embrace the beautiful uncertainty that lies at the heart of it all.
Imagine a world free from the constraints of limited energy resources. Imagine solving humanity's energy crisis once and for all. What if we could tap into a virtually inexhaustible power source fueled by something as abundant as seawater? A power source that produces no greenhouse gases, leaving our atmosphere pristine and our skies clear. Imagine a future with no long-lived radioactive waste, eliminating the burden of storing hazardous materials for millennia, and a power source inherently safe, incapable of meltdown, removing the risk of catastrophic accidents. This is the promise of nuclear fusion. the very same process that powers the sun, the source of all life on Earth, and every star in the cosmos. For nearly a century since the first inklings of understanding the atom, we've dreamed of harnessing this incredible energy source right here on Earth, building our own miniature suns. But if we already know how stars work, if we understand the fundamental principles, why haven't we built a working fusion reactor, a star in a bottle, here on Earth? The answer is both simple and incredibly complex. Fusion is one of the toughest scientific and engineering challenges humanity has ever undertaken. In essence, we're trying to create and then contain a tiny piece of the sun, achieving and maintaining extreme temperatures, hotter than anything found naturally on Earth, while also dealing with immense pressures far greater than those at the bottom of the deepest ocean, all contained within a perfectly crafted magnetic cage, preventing the superheated plasma from touching the reactor walls. The potential payoff? Clean, virtually limitless energy, a sustainable solution for generations to come. Energy that could fundamentally transform civilization, ushering in an era of unprecedented prosperity and progress. Energy that could lift billions from poverty, providing access to electricity and opportunity, and power our future, sustainably and equitably. Yet, despite decades of dedicated effort by scientists and engineers around the globe, commercially viable fusion power remains tantalizingly just out of reach, a challenge that continues to drive innovation. The core difficulty lies in the incredibly extreme conditions that fusion demands, pushing the boundaries of what's physically possible, conditions far beyond anything we encounter in our daily lives, in our homes, or even in most industrial processes. Achieving, and more importantly, maintaining those extreme conditions with incredible precision and stability, even for a few fleeting seconds, represents a monumental feat of scientific and engineering prowess. So, what exactly makes achieving controlled fusion so extraordinarily hard? What are the fundamental obstacles we face? The answer lies deep within the fundamental forces of nature and the sheer violence needed to overcome those forces and unlock the energy within the atom. To truly understand the magnitude of the challenge, let's take a closer look at the only working fusion reactor we currently know of, our very own sun. By carefully studying how the sun achieves fusion naturally, we can begin to truly grasp the immense scale of the scientific and engineering challenge we face in replicating that process here on Earth. Fusion, the process that powers the stars, might seem like an incredibly complex phenomenon, but the basic principle is surprisingly simple in theory. It's all about bringing atomic nuclei together under the right conditions. The core idea is to smash two light atomic nuclei together with such force that they overcome their natural repulsion and fuse into a heavier one. This fusion process releases a tremendous amount of energy, far more than any chemical reaction. This is precisely what happens in the sun's core, not just every day, but every single second. It's a continuous, ongoing reaction that sustains the sun's energy output. The sun, a giant ball composed primarily of hydrogen, possesses the incredible ability to create immense pressure and staggeringly high temperatures within its core. These conditions are absolutely crucial for fusion to occur. We're talking about temperatures soaring to approximately 15 million degrees Celsius. That's hot enough to vaporize any material we know of on Earth. At these extreme temperatures, matter exists in a state known as plasma. In this chaotic environment, hydrogen nuclei are stripped of their electrons, creating a sea of charged particles. Normally, protons, which are the nuclei of hydrogen atoms, repel each other due to their positive charge. It's like trying to push together the same poles of two magnets. You feel a strong resistance. But the sun's extreme heat and pressure, generated by its immense gravity, force these protons close enough together to overcome that repulsive force. When they get close enough, the strong nuclear force, a fundamental force of nature, kicks in and binds them together, fusing them into helium. This is where the magic happens. This specific sequence of fusion reactions, primarily the proton-proton chain, is the sun's engine, the source of its incredible power and light. Every single second, the sun fuses an astounding hundreds of millions of tons of hydrogen into helium. The scale of this process is almost incomprehensible. In doing so, it converts a small fraction of that mass directly into energy, according to Einstein's famous equation E=mc². This energy reaches us as sunlight, providing warmth and sustaining life on Earth. The sun's sheer size and immense gravity are what make this process seem relatively straightforward, at least from a cosmic perspective. On Earth, however, we lack that crucial gravitational force. Therefore, we must find alternative and ingenious ways to force atomic nuclei together with sufficient energy to initiate fusion. Replicating this stellar alchemy, achieving fusion without the benefit of a star's massive gravitational field, is the real and significant scientific challenge. We need to artificially create similar conditions to those found in the sun's core, the same extreme levels of heat and pressure, but within the confines of a laboratory. And that's where the difficulty truly begins, pushing the boundaries of engineering and scientific understanding to their absolute limits. So, let's delve deeper and see how we are attempting to recreate a star's heart right here on Earth, and the innovative technologies being developed to achieve this ambitious goal. The sun, a colossal fusion reactor in the sky, harnesses the immense power of gravity to compress and heat hydrogen atoms until they fuse. This process releases staggering amounts of energy. We, however, can't replicate the sun's gravitational forces here on Earth. So instead of gravity, we rely on cutting-edge technology and innovative engineering to achieve the three essential conditions for fusion. These conditions, often referred to as the triple product, are the key to unlocking fusion energy. First, ultra-high temperature. Second, enough pressure. And third, sufficient confinement time, the triple product. This refers to the duration for which we can maintain the plasma at the required temperature and density. Miss any one of these crucial elements and the fusion reaction simply fizzles out, failing to produce any significant energy. It's a delicate balancing act. Let's start with temperature. Achieving fusion on Earth requires heating matter to at least 150 million degrees Celsius. That's 10 times hotter than the sun's core, an almost unfathomable level of heat. At this extreme heat, matter undergoes a dramatic transformation, becoming plasma, a seething soup of positively charged nuclei and negatively charged electrons, all moving at incredible speeds. Next, confinement. Since nothing can physically touch plasma this hot without instantly vaporizing, we use powerful magnetic fields to suspend it in a vacuum, preventing it from contacting the reactor walls. This creates what's known as a magnetic bottle, a carefully shaped field that contains the superheated plasma. Magnetic confinement is currently the leading approach to fusion energy, but building a stable and incredibly strong magnetic cage capable of withstanding these extreme conditions is a monumental engineering feat. Finally, we must keep the plasma stable and confined for a sufficient amount of time, long enough for fusion reactions to occur and release energy, whether that's seconds, minutes, or even longer. The ultimate goal is ignition, achieving a self-sustaining burn where the energy released from fusion reactions is enough to maintain the plasma's temperature, creating a continuous cycle. But plasma is inherently wild and unstable, prone to turbulence and unpredictable behavior, constantly trying to escape the confines of the magnetic field. Therefore, taming these plasma instabilities and maintaining stable confinement is one of the greatest scientific and engineering challenges in the pursuit of fusion energy. Achieving all three of these critical conditions, ultra-high heat, immense pressure, and sustained confinement time, remains the central quest in the global effort to unlock the promise of fusion power. So, the question remains, how do we actually build a magnetic bottle strong enough to contain this superheated plasma and create the conditions necessary for sustained fusion? Enter the tokamak, a leading contender in the race to harness fusion energy. In the 1950s,